Welcome. My name is Lou. I steer the programs at the California Institute for Machine Consciousness. But before I tell you a bit more about us, I want to express what comes really from the bottom of my heart, which is an enormous thank you to the Internet Archive for hosting us tonight in this beautiful, sumptuous place. So thank you. To Brewster, to all the team, not only they are absolutely wonderful people and really helped us on a short notice to organize this, but their mission is absolutely aligned, at least, with my value, and I hope yours, which is to provide universal access to all knowledge. And this is actually done here by archiving in the servers that you can see just in the back, and some others that are tucked in other places in the archive. And it contains, and I'm sure you can feel right now the heat. Some of you have found the Internet Archive fans of the billions of web pages, millions of books, of text, of audio recordings and videos that are stored here. And this is truly a wonderful mission. And about us, so CIMC, the California Institute for Machine Consciousness. Can I have a little wave from people, team members, people, collaborators from CIMC? Look at them. You can find them after to chat. Exactly, that's why we organize these salons. We organize them every Thursday in San Francisco when we are here. However, tonight is quite special because it is the first event in a series that we have in the next 3 days that we are organizing to celebrate our official launch. Finally. Yes. So we are quite thrilled, to be honest. At least I am. And this is going to be very fun. And who would be better to kickstart this than our eminent scientific advisor, Stephen Wolfram, who is here tonight with Joscha, our dear executive director of the CIMC, to discuss what if we had bigger brains, which hopefully should advance after tonight, a bit more our understanding of consciousness. And I forgot to tell you that this is actually our mission, which is to formulate testable theories of machine consciousness, but also to build a culture and to build an ethics that is based on a deeper understanding of machine consciousness. The two are very important. Anyway, enough talked for me. I'll give it to you, Joscha and Stephen, and thank you.
If we think about this question, what would it be like if you had bigger brains? I'm not a neuroscientist. So my perspective on the brain is twofold. I'm a computer scientist, and this makes me very unsatisfied and skeptical when I look at this biological hardware. And the other one is the user perspective, and that is even less satisfying. And I feel extremely challenged with respect to my brain size. It's not making me happy. I don't fit in the stuff that I want to simulate with it. I have difficulty to use it in a way in which I want. It's really difficult for me to be uploaded on the substrate and deal with it. And it would be fascinating to have a better substrate. So if we look at the substrate, it's, well, in my case, I made an estimate based on my head circumference. It's probably 1.4 kilograms or something like this of head cheese that I'm implemented on. And if you look at the number of neurons, the typical estimate that's being given is 86 plus minus 10 billion neurons, and an about equal number of other cells that are playing supplementary roles and are probably also involved in some way. But most of them are in the cerebellum. And personally, I am not a cerebellum connoisseur. I think this is largely ornamental for motor stuff and so on. Basically, if you remove the cerebellum, people can still think and do things. And so it's only the tiny part that in the number of neurons that is the neocortex. And the neocortex is heavily interconnected. We have all these trillions, 100 trillion synaptic connections, which if you think about a synapse being something like 4-bit or so, it's similar to our large frontier models right now, if you think that the synaptic connectivity is the thing that matters. I don't know if this is what matters. Well, do you have opinions on this?
I don't know. I mean, the big surprise of recent times has been that, LLMs got to be able to do things that we thought were human-only type things, And the question is, how much does it matter what the detailed hardware is to be able to achieve those kinds of things? My strong suspicion would be it doesn't matter so much what the detailed hardware is. I mean, in terms of what's important in brains, there are people who think you need new physics to explain how human-like minds can work. I think one of the data points from LLMs is they probably put the last nail in the coffin of whether you need new physics. And the answer is you don't need new physics, I think. That might be wrong, and it's the circumstantial evidence is you don't need new physics. It really is just kind of the things that we kind of can imagine about bits and connections and so on.
There is sometimes this argument that for consciousness, maybe you need new physics, but for the other boring stuff, you don't need it. And don't buy into this argument, in part also because in new physics what it would give you is probably more speed. Right? Some classes of arguments might be faster, but this doesn't seem to be the thing that is holding us back in understanding consciousness. It's never, if the thing would be faster, it would wake up. We actually don't quite know if we can wake them up. Some people on the other side are saying we don't know if the LLMs are already conscious.
Right, and so, one might ask the question, just like there seems to be a threshold somewhere between cats and dogs and us, where you get to things like compositional language. And so you might also ask, as people often have, is there a similar threshold where suddenly the consciousness light turns on? What do you think about that?
I don't think that compositional language is the thing. Basically,
if
human being loses compositional language, they don't generally fall unconscious. But there seems to be a threshold, and I suspect that if you look at, say, gorillas and human beings, gorillas have a smaller brain than us, but there's a substantial overlap. So they see human beings with gorilla-sized brains, and they do fine. And the main difference, I suspect, is length of childhood. It could be that Chomsky's theory is correct, and there is some particular kind that is different, but I suspect that basically we see an order of magnitude more training data than a gorilla. We have much more...
Are gorillas conscious according to you?
Oh, yeah, clearly.
Okay. Yes.
Yeah, so that's not the issue.
Right. But so I mean, one of the issues, one of the things I'm curious about is, in terms of brain size, there are a few data points that we have. I mean, one data point is what are we humans capable of that is different from what the cats and dogs are capable of. Another data point that we have in recent times is the growth of neural net systems where, there are a series of thresholds that got passed. Back in the 1980s, it was, we can do, recognize digits with, a couple of million, connections and so on. Then it was, we can do, larger scale image recognition with, maybe, 10 million, 100 million connections and so on. And then finally we get to the modern LLMs where one's dealing with, 100 billion connections or something, and then we can get to do, a lot of linguistic kinds of tasks. So it seems anecdotally from what we've observed with neural nets that there are these series of thresholds of what you can get to with a certain effectively size of brain. And so the thing that I've been curious about is, it's a very frustrating thing. We only have the brain of the size we have, so to speak. But can we imagine what it would be like if we had bigger brains and what kinds of things would we be able to do? And so, for example, we have, something like compositional language, the ability to have a language where, like the cats and dogs maybe can understand the one word, fetch, sit, things like that. But we can have this much kind of richer way of composing words to make, much finer described concepts and so on. And the question is, what's the next level beyond that? And can we imagine what the next level beyond that might be like? And is that what we would reach is it purely a matter of brain size? Would we, naturally, if we could make, a brain organoid that had, 100 trillion neurons and was nicely organized and so on, would the brain organoid suddenly start doing this thing that is the next level beyond compositional language? Then, of course, the next question is, even if it's doing that thing, would we have a clue what it's actually doing? In other words, can we make, this bridge between what we, the way that we think about things? I mean, this is as a general matter, if we look at sort of computation in the world, there's computation that we do in our brains, there's computation that happens in the natural world. The computation that happens in the natural world is probably much more extensive than the computation that happens in our brains, but it's not aligned with the kind of computation that happens in our brains.
Do you suspect that there might be things on the planet that are smarter than humanity over long enough time scales?
That's a reasonable question. I mean, I think, you see, but this is what does smarter than mean? I mean, it's kind of we can observe certain features of reaching certain levels. Like we can say, oh, with our brains we can do certain kinds of computations, or we can describe certain kinds of things. I don't think I really don't think there's a single sort of linear path. The thing that's interesting about the brain size thing is that is a single kind of linear path. You just increase the number of neurons, what happens? But then the question is, are the things that happen, are they all kind of going in a path, like if you had it do an IQ test, it would get, score this amount this year, the next amount the next year, and so on. I don't think that's the right way to think about it.
Yeah. In a way, I think that intelligence is a misleading concept. Intelligence is the ability to make models, but it's usually in the service of control, and the actual game is agency. To which degree are you able to take charge of the future? So if we zoom out, we could say that evolution is an algorithm that makes models at some level, right? So you could say that the way in which nature implements itself over a large enough time scale is following some complicated parallel gradient descent and right? But the question would be not just how intelligent is evolution, because we are part of it, but could ecosystems, for instance, ecosystemic intelligence decide, oh, humanity was not a good idea, and take action against humanity and say, oh, we have to outsmart humanity, even though they're so smart on short time scales, but we come up with something on large time scales to get rid of this blight that is destroying the large ecosystem.
So what's the fitness function? Because if you're saying it's optimizing something,
minimizing the free energy, stability of systems of agency that are modeling themselves in the service of that.
Well, wait a minute. So in the end, people have often say that life on Earth was simply speeding up the redox reactions, so to speak. That's the only thing that life ultimately achieves, so to speak.
It's not just speeding it up, right? It's able to harvest entropy where simple chemical reactions cannot. So the opportunity for life on Earth is controlled reactors, that you can look ahead for the things that you're doing, that you add a little bit of energy to harvest more energy later, that you can produce extremely complicated catalytic reactions that require you to set up complicated stuff to make it happen.
Okay, but the sad fact is that we are a microscopic part of the biomass of the planet, and most of the biomass of the planet isn't doing what we see as being incredibly intelligent things. But to this question about what is, like these questions about the special thing that sort of we seem to have that minds have, and maybe there's something to do with consciousness and so on. As I was thinking about this bigger brains question, I was kind of wondering, what were brains for in the first place? Animals have brains, plants do not. One of the things that animals have to do is they are sort of things that can move around, and they kind of have to figure out, where am I going to move next? And so I think, one of the rather, in a sense, mundane functions of brains is you've got all this input data that's coming in from your world, and the thing you have to decide is, do I walk left or do I walk right? And it seems like a lot of the structures in the brain are rather mundanely set up to take, large amounts of input data from our eyes and touch sensors and so on, and sort of filter them down to the idea of, okay, every 10 times a second or something, we're deciding what's the next action we're going to take. which is a very special kind of computation. I mean, the computation that happens, in lots of things we might do in a computer, lots of things that happen in the natural world are not computations that are of this type that I think is the same kind of thing you're talking about whether you're taking all of this input data and then the main thing to say is, what should I do next? Now, I think you're implying that there's some kind of, that there's a notion of predicting the future, which I guess is the thing that I guess I have something of a hard time with is understanding, beyond the simple natural selection fitness function of make more of yourself, so to speak. I'm not sure what else. Are you implying that there's some other fitness function that's being applied to the development of, for example, life on Earth?
It's, the fitness function ultimately is produce structure that persists. That's the thing that's left over. If you envision yourself as an agent that could go into all the possibility paths from now on, so you could mutate yourself into something that becomes larger or smaller or more directed on the future, more or less risk-taking, more or less catatonic, right? And then you think about which instances of you are going to make it into the future, which are going to be the dominant ones. And that is, in some sense, a way to understand the fitness function over the set of all the possible organisms or structure-forming principles. Biological evolution, I think, is not the primary force in this, even though it's the only one that we know of that produces agency. But what's actually happening is the forces of self-organization, the possibility for something like biological evolution to happen, that it's play in the universe. Well, so when you have a puddle of entropy and you have enough noise, then there is a good chance that something forms that is able to exploit the entropy.
Okay, so that's an interesting claim. I mean, I think, one question is sort of what's special about life, for example. And I think the one thing that, is clear, you open a random molecular biology textbook, and it is full of descriptions of mechanisms, of lots of ornate things where this molecule grabs onto that molecule and does this thing and that thing. It's a remarkable technology stack, in effect, of all these detailed sort of structures that have evolved, and I see it as being this kind of bulk orchestration process that biology has managed to achieve, for which we basically have no theory right now.
Yes, I think what's special about life is that self-organizing software is running on it. So life is characterized by agency that is organizing molecules in such a fine-grained way, sometimes individual molecules that are addressed. Yet that's robust against many of these molecules disappearing and then recruiting new ones. And this is happening at many, many layers. And so this notion that software is an irreducible invariance, that you actually need it to explain the world, causal patterns are the actual invariants that can spread themselves over a large region of physical space and then lay claim to it, is crucial. And once I realized that, I realized, we are rediscovering the ancient notion of spirit. And so science gave up on this idea of spirit because they thought it's superstitious, instead tries to explain the mind and life via mechanisms, and despair, because the mechanism is the thing that you're seeing where particles are pushing and pulling. What actually matters, the actual invariance, is not the set of particles in the same way as it doesn't matter for money which physical particles are involved. What matters is that the causal pattern is stabilized and is able to sustain itself.
Yeah, I mean, I think, I found it a bit embarrassing for myself that when I was a kid, people would talk about souls and things, and I would say, but how can that be a scientific thing? What does the soul weigh, for example? Which is completely the wrong question. Yeah. Because the notion of a soul, so to speak, I think I see now as being kind of a thing where people were sort of pointing out the obvious, which is there's something to brains that is beyond the actual detailed physical instantiation of electrical signals and all those kinds of things. There's something that is this is the idea of abstract computation independent of the details of the implementation layer. And I think that's, it is interesting in terms of the sort of arc of progression of science that people perfectly well knew that idea long before kind of modern science came along and made everything mechanistic, so to speak.
Yeah, when my friend, the psychologist Dietrich Dörner, wrote his magnum opus, Blueprint for a Soul, I asked him, why do you use this word? It's just throwing people off with the superstitious term. And then he pointed me at Aristotle. And when you read Aristotle, you see the psyche is the form that imposes itself on physics, and it doesn't have any supernatural connotations for Aristotle. For him, this is a causal pattern that is structuring physics in a particular way.
But you know, this whole point about the computation, you know, this computational pattern is the important thing. You know, one of the questions about brains is, how much does the implementation layer actually matter? And this is a kind of core question, I think, for machine consciousness, because, you know, if the implementation layer, if it really matters that we have, you know, RNA molecules doing special things, or we have quantum effects in brains doing special things, then the notion that we will be able to make a thing like the consciousness that we have in our brains in a digital system is just not going to work. But if it is really the case that the things that's important about a mind is this kind of abstract computational layer, then it may not matter what the implementation layer is, just like it doesn't matter, you know, we can have lots of different kinds of computer hardware and we can still run the same software systems on those different pieces of hardware. And so I think, you know, that to me is like a foundational question is, you know, does the implementation layer matter, or is what's important about consciousness and so on this, you know, this essentially computational software-like layer?
Yes, we are both computationalists, but this doesn't mean that we claim that our computers can think. We don't know that, right? We think it's likely, but the claim of computationalism is separate. It's simply constructivism. We are saying we have to describe reality with constructive languages because that's the only thing that works. Right, so when we reverse engineer our own thinking, we have to realize that our brain is using models that can be implemented in the physical universe and that obey mathematical principles. And this is what computationalism basically means. It's a statement about the nature of representation and the nature of thinking about the world of perception. But the strong form of computationalism is that the universe itself, to the degree that it's comprehensible and observable, also needs to be a computational structure.
Right. Well, this is something I've obviously done lots of work on. Last 5 years or so has been kind of a breakthrough moment for that, because it became clear that I think we figured out sort of what the machine code layer of the universe is like, and it's, you know, can be described computationally. I mean, you should understand, you know, if you think about in the big picture, what's the point of science? What's science trying to do? You know, the universe is doing what it does. We have things that we can think about with our minds, with our rather finite minds. And in a sense, natural laws are an attempt to find a bridge between what the universe actually does and what we can kind of make a narrative for in our minds.
Let's get back to this. I would love to discuss this machine code for the universe. But first, let's go back to this question of architecture that you brought up. So when we look at a multicellular organism where the individual cells can send conditional messages to other cells, as computer scientists, we see a Turing machine, right? So we see something that in principle can execute arbitrary algorithms. And under evolutionary conditions, if this makes sense for a multicellular organism, it should discover some general learning algorithm that builds structure on it. And so the question is, what are the limits of a thing for representation, learning, self-representation, experience that doesn't have a nervous system? So when we think of a nervous system, the difference of a nervous system to normal intercellular communication is you have these axons, which are like telegraph wires that go through your body and that break its topology, that basically like little wormholes in the topology of your body. And in order to send signals over this long distance, you need to encode them into Morse code, into spike trains. And so they are very stable over long distances, but they don't use the same language as normal cells when they talk to their neighbors. Right? It's not RNA molecules or EM emissions or whatever cells are like to talk to each other. Or chemicals, it's these spike trains.
Well,
and, so you would have a second operating system that is evolving on there, that speaks a different language.
I mean, there are lots of different communication mechanisms in bodies. I mean, you know, the bloodstream is another thing that globally transports information around the body. The immune system transported by the bloodstream does that. Mm-hmm. So it happens that's somewhat slower than, you know, nerve transmission and so on. But I think it's, you know, it's the freeway system, so to speak, of communication in bodies. But I think to this question of whether that's somehow an inevitable feature of biology, you know, I recently ended up figuring out, I think, kind of an interesting foundational model for biological evolution. And so what happens, okay, so the first thing to say is there's a very fundamental phenomenon that I call computational irreducibility, which you know, I talk about all the time because it's a thing I discovered, which I never expected. I discovered in the early 1980s And it took me years to sort of come to terms with it. But the question is this: if you have some simple program, some trivial thing with a bunch of black and white squares or something, and some simple rule to describe how those squares should be updated, the question is, if the rule is simple, what is the behavior? What can the behavior of the system be like? And my initial intuition is, in order to get complicated behavior, you need a complicated rule. If you have a sufficiently simple rule, the behavior will somehow be always of limited complexity. Okay, this turns out to be wrong. Turns out that even with incredibly trivial rules, you get things that are as complex as anything, so to speak. And that led me to this idea of principle of computational equivalence, that you kind of get above this threshold very quickly where you're achieving sort of as much computation as anything can achieve. This leads to the idea of computational irreducibility. So the question is, if you've got some system, even a very simple program, and you say, what will this thing do after 1 billion steps? Well, you can find out by just running that 1 billion steps and seeing what happens. The question is, can you jump ahead and be smarter than the system and say, I know what that system is going to do? In traditional mathematical science, that has been kind of the big name of the game. That is, make predictions, be able to say, oh, we know the equations now for describing the motion of a planet around an idealized star. Now we don't have to trace all those orbits. We can just use the formula, make an immediate prediction. So what computational irreducibility says is that in the kind of computational universe of possible programs, it is completely ubiquitous to find situations where the only way you can find out what will happen is essentially just to follow the steps and see what happens.
I think free will is in some sense a representation of computational irreducibility. It's a representation that you yourself are making, that you cannot predict your own decision before you make it. So you act at the boundary of what's known locally from your own perspective. And you cannot predict it because you have to run the universe to this point. You have to get all these factors in there. But an interesting question is, why can we model the universe at all? And I suspect that's because the n-body problems and so on, all these famous examples where you cannot look very far ahead easily analytically, and you have to run a simulation that actually gets to this point, we have difficulty to predict the outcome. And so we have difficulty to play with it. And most of the structure in the universe is control structure. It depends on some part of the universe being able to predict what another part of the universe is going to do. So if you look at your own organism is coherent because parts of your organism can predict what the other cells are going to do. Otherwise, your organism would fall apart. So your organism evolves in such a way that it becomes predictable to itself to a very large degree. And the fact that most of the structure that we see, whether it's cells, molecules, societies, operating systems, whatever, has to be built via such control structures. That's the reason why it's so learnable. And so in many ways, the computational irreducibility is the boundary against which we run, but we don't run against it all that often because we can, for the most part, ignore it because nobody can do something with it.
Right. Well, but I think what happens is, looking at the universe and how it's built up, sort of most things about it are computationally irreducible. But one feature of computational irreducibility is there are always, within any computationally irreducible system, there are always actually an infinite number of pockets of reducibility, places where you can make a particular statement about what will happen. So, if we look at the typical thing of, water in the glass or something, the molecules in the water are doing all these computationally irreducible, complicated things, but yet there is a level of thinking about and looking at the water that is quite predictable. It will pour in this particular way. And I think what happens, and it's a very fundamental thing about the universe and our role in it and so on, is that we kind of explore pockets of reducibility within this otherwise computationally irreducible world. And the very fact that it's set up that we are living in these pockets of computational reducibility. If it wasn't for that, nothing about the world will be predictable. When we find a scientific law, it is an example of a piece of computational reducibility. That's sort of what allows us to take what the universe is actually doing and crush it down to the point where it can fit in a finite mind, yep, and we can think about it.
Let's bring this back to the bigger brains. So if we think about what brains have to do is they have to find ways to effectively reduce the complexity of the world. So we have to find regions where we can make good enough approximation with the tools that we have, and we gradually build up those tools. And the better the tools we have, the more fidelity do we get to the ground truth. When I was young, I thought that insects have a very simplistic, mushy representation of the world. Maybe it's just flow fields or something. And then I realized the way in which we build textual representation is generator functions, similar to something like the Mandelbrot fractal, where you basically use some relatively simple origin function that gives you as much complexity as you want. But the complexity that you are seeing
it's kind of like a shader,
fractal, right? It has, you can get infinite detail if you want, but this infinite detail cannot be used to model reality. To basically align this fractal with reality means you have to keep it subcritical. You cannot get it to the point where it fully fractalizes. You need to keep it in a region where you parameterize it a little bit and then gives you a shape that you can use as a model for reality. So for instance, some kind of texture that looks like a good enough compression of what you are seeing on your retina. And I suspect that ants are also using fractals to depict reality. So they're like us, our world, it has infinite detail. It's just the fidelity of this fractal is probably much lower than ours. This means the horizon after which stuff is meaningless and doesn't, the structure is not predictive of the surface that they're walking on anymore. It's probably smaller than ours.
That's an interesting claim. I mean, I have to say,
I also don't know that.
Yeah, I mean, it sort of reminds me of, shaders that one uses in computer graphics where you specify the program and it kind of fills in all the details of what every pixel should be. But I have to say I'm skeptical about, the fractal ant, so to speak. I think it's I mean, in terms of, well, the question is what its internal view, I mean, this question of what the internal view on the part of the ant is about the surface that it's walking on, I think that's, I mean, ants have about 50,000 neurons, I think. And you can, there's sort of you could imagine sort of sampling a piece of, mechanistic interpretability, so to speak, for an ant seems as challenging as it does for other things.
I don't know how many neurons, does anybody know the number?
For what,
Rick?
for an ant?
For ant?
I think that's about right. Maybe it's 100,000, but I think it's of that order.
Yeah. I thought it's a
that
million.
many?
Yeah, I thought it was much more.
What's that? Okay, we have it. It sounds like a bidding war here. For,
No, it's a million, I think, or somewhere in the ballpark, right?
I think it's less than
A few million.
Okay. Anyway,
We would have to run simulations to figure it out.
Right. I mean, of course, one of the interesting questions these days, now that the fly connectome is known, there's this question of whether which is again related to the whole sort of consciousness issue, is if we know people sort of talk about if we knew the connectome of our brains, would we be able to simulate what our brains do? And the bad case is the nematode, where we know we've known for 30 years or something what the connection of the neurons is, but yet you still can't simulate what the thing does. I mean,
Not sure how important the connectome actually is. I suspect that the connectome is largely stochastic. And what matters is that neurons under certain conditions are going to hand on signals in a certain direction. And so I suspect that basically three paradigms by which neuroscientists seem to be looking at the question of representation. Roughly speaking, there is the soup paradigm. It's a bunch of chemicals in a soup, and if you change the chemicals, representation is changing. I'm dramatically simplifying. The other one is the circuitry paradigm. So you have all these wires and switching elements between them that integrate and fire, and might have some coupling with each other, but for the most part, it's circuitry. And the third one is vibes. So it's waves that go through this neural ether and interacting with each other. And the individual neuron is basically a node in a stochastic lattice that is taking in these signals and modulates them conditionally and then passes them on. And all these three stories are true to some degree, right? They're all part of a larger story of how representation works in the brain. And it's difficult to understand in which proportion and when one of the stories elucidates what's actually going on. And what I'm not quite sure about is how important the architecture actually is, right? We know the human brain is extremely differentiated in these different parts and they have very different roles. But is this because we need very, very different circuits to think at all? Or is this because the brain is a machinery that is highly optimized for its tasks. So our reaction time in reality matters a lot. And so one hop from one neuron to the next is very expensive. If we have one more, then our reaction time is going to be 20 milliseconds or something less. And so we want to minimize this. And this means that the different circuits that we build in the brain are not going to be general purpose. It's like in early computers where we have a special circuitry that does floating point numbers. And only that. And now we basically put everything on the GPUs and it becomes more general purpose again.
Well, I mean, my impression is that most of what happens in brains is not particularly special purpose. There's special purpose I/O for, vision, auditory system, etc., things to do with motion and so on. But it seems like, the general claim of, just sort of developmental neuroscience or whatever is, if different parts of the brain can take over from other parts of the brain, even though it is a surprising and interesting fact that functions are somewhat localized in the brain.
Yeah, but you cannot get the cerebellum to take over for the cerebrum, probably. Right? But for certain parts, you can say you can scramble the brain early on in development, and it's going to organize into something that is eventually going to figure out how to work somewhat.
Well, so an interesting question for that is if you make a somewhat disorganized organoid that you just grew a bunch of, nerve cells from stem cells or something, will such organization, if you could feed it input, would such organization spontaneously, would it effectively organize at a software level, even though at a hardware level it's a big mess? I don't think one knows the answer to that. But I think because that's not what, in biology, that's not what ends up happening.
Yeah.
But
I know some people which work on this topic. I find it mildly revolting, but it's fascinating.
Right. I mean, there's one company I know where the obvious question you ask of somebody who has a company that makes brain organoids is, whose brain is it? And the next question to ask is it yours for the CEO? And the answer is usually yes. And it's so at least they. But
we also have this phenomenon here in Silicon Valley where people watch Black Mirror and say, "Oh my God, this is a business case."
No, I think. But coming back to, let's see, we were talking about life and sort of the specialness of life and so on. And maybe we can, one of the things I've been curious about is it seems like, one of the things about life is it's sort of a bulk orchestrated even at the molecular level. Every molecule is, at least every large molecule, is sort of operating like a machine which is interacting with other large molecules and so on. It's not, the kind of thing that you see in a typical liquid where just molecules can be modeled as just bouncing around randomly, so to speak. And so I do think that there's a sort of fundamental scientific thing that needs to be invented that is kind of the theory of bulk orchestration. And so, we have from 150 years ago, we have statistical mechanics, the theory of what happens if you just have sort of molecules bouncing around randomly. I mean, a thing that I happen to be working on right now is trying to understand sort of the effect when you have something which was sort of adapted. It has, in this model for biological evolution that I made recently, you can see these kind of structures that get produced by kind of, forcing it to adapt to some fitness function. What happens is that if you look across all these different rules and you say which ones are adapted for some fitness function, there will be a character to the things that are adapted that is different from the character of the things that were not adapted. And what is really strange, and really frustrating because I can't figure out how to think about this, is you look at these pictures and they look very lifelike. They look very kind of organic. There's something about them that kind of reminds one of life. And it seems like that seems to be the, I'm guessing that there's sort of an essential kind of character to kind of lifelike things that is different from what we see in most of the rest of the sort of computational world. And it has to do with these things that were sort of adapted for a purpose. Now, it's a tricky business, when you describe a thing and you say, this happens, okay, why did it happen? Well, one explanation can be, the projectile followed this parabolic trajectory because it satisfied these laws of motion, and at every moment, mechanistically, the projectile moved in a particular way because of those laws of motion. That's one explanation. Another explanation is, it's following the path of least action. You're saying basically the projectile is satisfying, is achieving some purpose. And essentially anything you look at, you can describe it in terms of its mechanism, and you can describe it in terms of some kind of purpose. And it is a challenging thing to say, you know, when are things better described in terms of purposes, when are they better described in terms of mechanisms?
I think what makes life special is it's inside out rather than outside in. When we build designs from the outside in, like say a computer game, the shapes are as simple as we can make them, right? We start with geometric primitives that have little detail and so on, and we add detail and make it smaller and smaller until you have enough detail. Life starts with detail and becomes larger and larger. It's all detail. It's all detail that is organizing the structure from the inside out, colonizes the environment, and builds itself into the best thing that it can. And the adaptation goes in several directions. One of them is to make the detail work in a way, but the other one is a generalization. So the stuff that you learn can be used somewhere else. So you modularize, you are trying to generalize the types of cells that you have and so on, homogenize as well.
Well, I mean, you know, one of the things you were saying earlier, which was sort of, it's inevitable that you end up with things like nervous systems. I wonder if that's true. I mean, I think the thing that has surprised me looking at biological evolution, looking at these simple models, is, you know, the thing will end up with having some structure. It'll have little triangles that have particular borders around them. It gets to that level. Then it builds on that idea to make bigger triangles, more triangles, et cetera, et cetera, et cetera. And so you see these different possible sort of progressive inventions getting made and getting built on. And I think that that's, you know, the thing that I've been really struck by recently is you end up with these, you know, computationally irreducible patterns where you say, why did it do that thing? Well, you can't really explain that. You just say, you run it and it sees what happens. The thing that I've been struck by recently is, you know, you open a typical biology textbook and it's describing all of these mechanisms, all these detailed things. And I have this vision that basically it's just describing one of these computationally irreducible patterns, and it's got all these complicated words, and it's, you know, I was thinking of getting an LLM to take one of my little patterns and have it write something in the style of a biology textbook that kind of explains what's going on. And it's, you know, biology is this kind of frozen example of computational irreducibility that is important to us because it is what makes us the way we are, but it's this question of whether it is the only way to achieve some overall course fitness function. I really don't think so. I mean, I think that, and you know, this question of what features are in common, you know, this question of what features are in common across all adapted things, my guess is that there are some general principles that are in common across all adapted things that are kind of analogous to the things that are in common across all things where there are just a lot of different elements, like molecules bouncing around. I mean, the big thing that's in common in that case is the second law of thermodynamics, law of entropy increase, the fact that it is typical for all these different elements to sort of behave in a way that to us, we just say it seems kind of random.
I think that adaptivity is not the only thing that's interesting. In some sense, stubbornness is also interesting, resistiveness. Right? The fact that we have big heads is in part because we have so much bone in our heads, so we can deal with the fact that we have to go our own way and break through walls and use our intelligence to get away with it, rather than to adapt. And you can adapt, and if you adapt very well, you can get away with having a much smaller brain. It seems that the Neanderthals had larger brains than modern humans, and maybe this was because they needed them, because they lived in smaller groups, that they needed to be intelligent, individually more smarter than today's hive minds, where lots of people are offloading their intelligence into other people.
Well, I think, you know, one thing about brain sizes is pure, you know, number of neurons and things like that. You know, whales have bigger brains than we do. Neanderthals had bigger brains than we do. I kind of think that so there's a general rule. If you look at the mass of an animal or the volume of an animal, the size of the brain scales roughly like the 2/3 power. Okay, so why is that? Well, I'm guessing the reason is because the 2/3 power is basically the surface area of the organism, and the number of touch sensors is proportional to the surface area, assuming the touch sensors are basically the same distance apart for all organisms. So I think the first level of kind of what you know, the amount of neurons is just, you got to be able to have all the sensory inputs. Then what happens is then there's a bunch of, there's in our brains, there's gray matter, which is the bodies of the neurons, and there's white matter, which is basically the wires. And as you go to bigger brains like ours, it's more and more wire. I think there's a 4/5 law of the amount of wire relative to content, so to speak, that happens in brains.
So we should be able to calculate a maximum size of a brain that you can build with an architecture like ours. And also, basically, think about alternate architectures. What I find interesting, if you look at, there are several animals which have larger brains than us. And was wondering why elephants are relatively stupid compared to us, because they have larger brains and they have long childhoods like us. But turns out it's mostly cerebellum, not cerebrum. So their cerebrum is actually smaller than ours. Maybe that's part of it. And another thing is, imagine that you could make your brain larger while retaining your mind. So you morph your brain, you add more tissue and so on, and you colonize it. At some point, there is probably going to be diminishing returns. Maybe it's difficult to become coherent if you have a larger brain. Maybe there's some kind of Goldilocks size. Can you flip? So if you think, for instance, cats react in something like 20 milliseconds. They have super short reaction times. And for us, the reaction time is more like in the area of 160 to 200 milliseconds. And elephants have like 300 milliseconds reaction time. And so it's tempting to think that part of the reaction time is the result of your brain becoming larger, and you need to, in your conscious mind, to synchronize everything in your working memory with all the other parts to make it coherent. So maybe there's a trade-off that you have to pay. The larger your brain becomes, the more difficult it becomes to create a coherent state, and the slower it's going to become.
Yeah, I suspect that's true, that the bigger the brain, the slower it runs. But that doesn't, by the way, I'm sort of reminded by this. When the iPad came out ages ago, for very silly reasons, I got into the question of, can you make a game that a cat can win against its owner? Because it turns out there are many practical problems about behavior of cats and things like this. But I was also really curious, if a cat could do Minecraft, for example, what would a cat build? And would we understand the structure it built? I mean, you say elephants appear to be stupider than we are, so to speak. There is it's hard to make that statement.
There is a game that they can win, which is control. So basically, I notice when our cat looks at a family member, the family member cannot look away until the cat looks away. So she hypnotizes people, and she is also able to train my family members to do exactly what they want, what she wants. And that's really interesting. It's not that she is super intelligent, but she is able to control us. She's also very good at reading the emotional state of people. And I suspect it might be because the cat is susceptible to micro-expressions and so on, because she has shorter reaction time.
Oh, just think what the AIs are going to be able to do.
Yeah. But architecture matters too, right? Cats are faster than snakes, and snakes have smaller brains again, but they have reptilian brains. And then bird brains might also have different architecture, have different way in which the neurons are acting. And so you get, with a much smaller proportional bird brain in terms of volume, much more intelligence.
I mean, the question is, so, the architecture of our brains, I think, at the level of primates, brains become crinkly and so on because they want to have sort of large surface area but not so much volume, and that's it's a trick for getting not such long connections and so on having to be made. But I think the thing that is tantalizing and frustrating to me is, imagine you scale up the size of the brain, and presumably you scale up things like the working memory in the brain, then what starts to be possible? And one question, I think, oh yes, can brains run code? There's a good question. Okay,
back. Can you go to the brain runs code? No, it's
one more.
It's further.
Maybe one more? No, we're still on Wales.
One more.
There we go. Can brains run code?
Yes.
Okay, you've raised several different points there, I think.
Yeah, so in your essay you wrote that we cannot run code, and I think that's not true, right? When I write an algorithm, I simulate this algorithm in my brain. I cannot run every algorithm that I can run my computer, and it's mostly because my stack is so small.
Yes.
And I cannot keep that many things stable, and also my working memory capacity is, this controllable part of it is small.
Right. I mean, the fact is, brains, when you say you run code in your brain, I mean, as a person who's, spent my life writing code and creating languages to write code and looking at, I mean, I am humbled by how little I can do in my own mind. It's just like, we build Wolfram language and Wolfram alpha and things like this, and you see the same issue for LLMs. LLMs can't do in their mind, so to speak, the kinds of things that are trivial for us to do computationally. It's a different build-out, so to speak. What gets done, what is easy to do with systematic computation is not the same kind of thing that brains and brain-like things easily do.
Yeah, but part of it is your attention. And I remember reading a Wikipedia article about Asperger's, and it was described as this developmental disorder. And you see this kid on a photograph in Wikipedia, which looks at some kind of Lego toy thing and is fascinated by it. And it's characterized by something for half an hour thinking about some constructive problem. And you think, right, for us that's normal. Oh, okay. And this goes further, there are savants which have extraordinary attention and teach themselves to do mental arithmetic at a superhuman level, right, compared to what normal people can do. And I think that's because they have enough attention to train code into their brain, to basically build a mental abacus. If you think about how an abacus works, you learn very simple algorithms into your motor system, and you use the abacus itself as a memory. So you take the state of the abacus and you manipulate the state using very simple algorithms that you just train into your fingers, and as a result you can do square roots and other things. And if you are able to train the same state into your brain, you can basically train yourself to have some kind of mental abacus that performs certain operations. You just need to have enough attention on that stuff, and most people find it so boring that they cannot attend to it. That's one of a way to think about it. But the other thing is when I am executing a plan or making a plan or writing code, I observe that itself, that is an execution that is happening in my brain. There is some kind of hierarchical scripting language that my brain seems to be doing. There is some executable stuff, right? And it's a particular language that my brain is using, and that language gets extended over time. I add new constructs to it. I found that when I teach computer science, there are certain abstractions that we get in computing that are not part of the common way in which people think about thinking. And the Sapir-Whorf hypothesis is this idea in linguistics that the way in which we think about reality is mostly shaped by our language. And this idea of this strong social constructivism that sometimes is associated with this might be wrong. I suspect that language is ultimately going to follow the needs of the speaker and the needs of the thinker. So if people see a certain phenomenon and you don't teach them a word for it, they will come up with a word for it or a way to use their language to express this. But how the computer science languages, the computing languages, programming language are an example for the Sapir-Whorf hypothesis, because they don't differ in what they let the computer do. They differ in how they let us think about what the computer should be doing. So there are ways to organize our own thinking about programs. And so there is an level of abstraction, like for instance, a variable. What is a variable? Not all people understand what a variable is. The next thing is a pointer. And then you have something like, say, recursion or closures. And successfully, these concepts become more complicated to wrap your mind around. And when it clicks, you learn an abstraction that teaches you some meta way of thinking, some way to write your own mental code and to decompose problems.
Right. Well, I mean, I've spent a large part of my life doing language design for our computational language. And, one of the things that is interesting is the way I view what I'm doing as is providing sort of a way to lead people to think in different ways. In other words, it's people haven't realized yet that language design, they sort of have realized in some cases, but not in the computational case. Language design is a way of molding thought. And, I know for, at a very practical level in building Wolfram language and so on, over the last 38 years or whatever, there are things that I introduced years ago, which even I didn't understand that well. But once they're in the language, you kind of get used to them, and then you can start thinking in terms of them. I mean, I think that it's a kind of a sort of cycle of things. Like you have a bunch of things that of a particular form, and in human language we then get, a word for a chair, for example. Once we have that word, we think in terms of chairs. We're going to make more chairs, and that, it becomes, I think words and so on become a sort of a way of concretizing the concepts so that, within our brains, things about that when we think about something, a glass of water or something like this, there's some complicated pattern of nerve firings in our brains. If we want that complicated pattern to be transportable, even through time for ourselves, if we want to remember what it was that we were thinking about, we're not going to remember the full detailed pattern of nerve impulses. We're going to remember some encapsulated, kind of robustified concept. It's the same thing when we want to communicate, when I'm trying to communicate something to you, there's some pattern of firings in my brain that will be different from the pattern of firings in your brain, but I have to package up the thing that comes out of those pattern of firings in my brain. I package it up into this sort of robust thing that is a concept that I can represent it as a word and so on, that I can then transfer to you and you can unpack it and maybe get something which is a pattern of nerve firings particular to your brain that is somehow corresponding to the pattern of nerve firings in my brain. But I think, this question of, one of the things that is remarkable about brains is that we do have this single thread of experience. It could be the case that in all the 100 billion neurons in our brain, that lots of them are doing their own thing, and that we would not have this idea that there is a one definite thread of what we're thinking about. I think that's we imagine that there's sort of the unconscious brain that's doing all of these different kinds of nerve firings and so on, but somehow this thread of consciousness that is pulled out of that is this thing that has this sort of coherent story about what we're thinking about, and in the end, what actions we should take based on what we're thinking about.
Yeah, I think this kind of information preservation in our mind, where we can reconstruct the steps where we're coming from, might be tautology, in the same way as information preserving in the universe is maybe something like a tautology, because the information that gets lost, we cannot remember it. The stuff that doesn't make it into the future is the stuff that is not here. So we will only reconstruct the past that has left traces in the present. And so it's very difficult to make sense of stuff in terms of gaps that might be there. But for the brain, we can look at potentially at alternate paths. We see this in the LLMs, that when the LLM is producing an output, it often in parallel looks at many options. And then in the end, many of these options are discarded, and you get an output in the end. I suspect a similar thing is happening in the brain.
To be realistic, for an LLM, we don't know much about what's happening inside. We do know that in the end, it is picking, there are 50,000 possible tokens. What's the probability that it assigns to each one? Then the outer loop basically is saying, well, I'm going to pick, either the most likely one or the one with some probability distribution based on the distribution of, so that LLM-like activity is actually pretty similar to what brains end up doing. There are lots of things that happen inside. There are lots of, I think in the basal ganglia and so on in the brain, there's lots of sort of inputs coming in, and then there's sort of a majority vote taken, it seems, that says, here's the thing to actually do. These are all the things you might do. Let's pick the thing to actually do next, the word to actually say next or whatever.
It's hard for me to say how analogous this is to the brain. There's this idea of the universality hypothesis, which says that the structure that you learn does not depend on the algorithm or so much, but it depends on the structure of the problem. And Chris Olah discovered this when he did mechanistic interpretability and more or less started to create the field while he was working at OpenAI, and saw that all the different vision models are learning the same feature hierarchy. And it seems to be the same feature hierarchy that the brain is learning at the low level in the visual cortex. And so this gave rise to the universality hypothesis, which basically means that the structure that you learn really depends more on the problem than on your architecture. And so it's not really the firing pattern, because the firing pattern does depend on the architecture. If you have a smaller brain, you need to fold the problem in a different way. Maybe you need to map a higher dimensional space into the lower dimensional space of what you can represent in your brain and multiplex it in a clever way so you don't get that much interference. But the activation pattern will then depend on your brain architecture. But the function that you learn is going to approximate the same control structure or the same discriminator. And when we study this, we can, with mechanistic interpretability, often find out what kind of rule systems are activating in the neural networks. There's now a lot of research happening in there. But I don't think that the neural network is very much like a brain. Right? The brain is not a 100-layer network that is mapping a prompt context in tokens to the next working memory context in tokens. Instead, basically, the LLM is more like a transition function between brain states that are abstracted as if there were tokens. Right? And our working memory does not contain tokens as such. It's something that would be much deeper in the neural network, something that is more abstract yet regularized. So there's some kind of language of thought that we seem to be using that is parallelizable and executable, maybe more regular than a poorly trained neural network.
Well, I mean, there's this question about sort of why does the LLM work at all? And, you know, my strong belief about that is the LLM is sort of taking advantage of regularities in language that, you know, we didn't happen to have ever recognized. You know, we well know that there's sort of syntactic grammar of language that, you know, in English sentences go, you know, noun, verb, noun, and so on. But there's also a more complicated construction kit of which noun, which verb, which noun. And you can sort of imagine having a kind of a structure for a sort of semantic grammar that describes that kind of construction. And actually, that sort of, in a sense, that might be the essence of what the LLM learnt. It did it in this fuzzy way with neural nets and so on, but in the end, what it's learning is this kind of set of rules for how you put sentences together. And actually, I had this project, which I started long ago, to try and figure out how those rules work. And actually, it's helped a lot by LLMs. LLMs make it tactically much easier to do that. And I can't yet tell you for sure that this completely works, but this is a project that's on its way, so to speak, to try and figure out what is the essential thing that the neural nets learnt that allows them to do LLM-like things. But I think that, I mean, to this question of whether there is, I mean, you know, to what extent does the substrate matter? To what extent are brains fundamentally different from neural nets and so on? And are there kinds of things that brains can do that neural nets will never be able to do, and so on? But I think the thing that I was curious about in the kind of bigger brains question is what, well, there's this question of what kinds of overall things can we say about what either brains or neural nets do? What kind of overall sort of theoretical things can we say about what they do? And things like the construction of language and so on is an example of a big picture thing we can say about what brains can do. So there's a question of what other big picture things can we say? You know, what is the, you know, in neuroscience, for example, we might say, what's an intermediate description level between the level of talking about individual neuron firings and the level of talking about psychology, for example? What are some intermediate statements that we can make about what brains do?
When I was working in Ian Witten's lab in Waikato in the 90s, he gave me the task of finding grammar in an unknown language. And
in what?
In an unknown language. And the unknown language I used was English because the computer didn't know it, but then I also tested it with other languages. And the idea that I had was to compress the sentences on a tokenized level where I would turn every word into a token and compress everything in this way. And then look for a mutual information measure that would allow me to optimally reduce the number of bits that I would need to encode the sentence, and in this way discover structure. And I found that with a relatively simple mutual information that was looking at pairwise connections, I was able to almost always discover the semantic hierarchy of the sentence. And this was especially useful in ambiguous cases, like when you have a sentence, I see the Statue of Liberty flying over New York. A pure grammatical parser gets it wrong per default, but a human being thinks it's much less likely that the Statue of Liberty is flying than I am flying. So it interprets in a particular way, and the statistical model interprets in the same way as humans would do. So it's disambiguating all these sentences correctly. And I was looking into this, and I thought if I could do more statistics, and I couldn't because I only had 2 gigabytes of RAM on my computer, and putting it in a hard drive made it too slow. I thought I would be able to discover semantic structure. And I later abandoned this kind of study because I thought NLP is boring, and I wasn't smart enough to realize if I continue doing this, we can just use language to recover basically all of the semantics. But I was also not surprised that it was happening. I was personally much more interested in a developmental approach and understanding motivation and perception rather than understanding how to extract semantic structure from text alone. I thought that was boring. But so I was not smart enough to realize the value of this. I mean, I was not alone in this. It's really depressing when you realize that LLMs, in the way in which they exist, could run on a 286 computer.
Yeah,
if we had known back then that this is possible, we could just have bitten the bullet and spent $30 billion to train a GPT-3 level model, and we would have been able to talk to our computers in natural language a decade earlier.
Right.
I mean, it would be so valuable.
This is the kind of, it's a large part of the story of the advance of science is, it is non-trivial to get the right intuitions. And often, I know in my own, like I mentioned, my sort of recent work about biological evolution, I started doing those experiments in the mid-1980s. I didn't manage to make them work. Now that one has the information that machine learning works, I went back and redid those things, pushing harder, and turns out they worked. But you needed to have that sort of empirical fact that machine learning is possible, which was kind of the surprise from 2011, 2012 type time frame, that it wasn't, these things are sort of, you make these discoveries and then that opens up new intuition. I want to say one thing about sort of bigger brains and computational language and so on. One of the things, if you look at sort of history of formalizing things, one of the formalizations was logic. And, from the time of Aristotle, we had syllogistic logic of, this was sort of a pattern of how arguments work. There are particular patterns of how arguments work. Okay, so from syllogistic logic, we wait 2,000 years, and then we get Boolean algebra in 1840s, where one sort of turned kind of logic into this mathematical algebraic kind of thing. Then you wait another 100 years until you get to, Shannon and kind of, Boolean algebra and switching circuits. And then now we have computers with, CPU chips with billions of logic elements on them. So one's gone from the formalization of arguments at the time of Aristotle, where one has sort of the structure of logic, to the sort of the systematization of it in Boole, to now, there's a billion logic operations, and we can do all these things with computers. And so the question is, when we formalize sort of things about kind of computational language, when we formalize those kinds, if we can formalize kind of everyday discourse in some kind of computational way, that's kind of like it's kind of basically the Aristotle level of going from all things we can say, rather than just the structure of arguments, but all things we can say to some kind of formalized version of it. And the question is, when one starts with that, you formalize things in the world that way, then what is the analog of what we now can do with computers, which went from these formalization of arguments that was logic, and then we build on top of that. So, for example, this is the thing that I'm wondering if this is sort of a clue to what to what we could do if we had kind of if our brains were more capable. Could we go from this sort of what's the kind of thing that we would get to if we built, just like from sort of thinking about logic, we can get to computation and computers and so on, thinking about this sort of computational formalization of the everyday world, what is the thing that builds on top of that? I mean, there's some very straightforward things, like you can take, legal contracts and you can turn them into computational kinds of things, and then you can expect to have sort of vast towers of these things that you couldn't do if you were just, doing them as sort of written documents in natural language and so on. So this is just one direction of kind of thought experiment of what could you do, what is the thing that you could build if you could formalize sort of everyday discourse in the way that Aristotle managed to formalize, the structure of arguments and so on.
Yeah, I think Aristotle could see that we are not accessing reality directly. A lot of the philosophy that existed before that and also after that assumes that the reality that we experience is the world, and that this world is pretty much the physical world. And Aristotle distinguished the physical world from what we perceive and the operations that we make on these representations. And these operations that we make on these representations are mathematical operations. And the way in which we can understand mathematics is that you perform operations on the smallest parts of discernible differences, which are these bitwise operations that are for instance, Boolean logic. And once you have Boolean logic or other logics, there are many operators that you can use, but NAND is in principle sufficient. Once you have a NAND operator, you can recover all the others, or you can use combinators or other ways to define this lowest level. And then you can scale this up to build arithmetic. And with arithmetic, you can then construct arbitrary models in continuous domains. And the reason why the neural networks works is because it decomposes a computer program in a differentiable function. And this differentiable function works by saying I do 100 steps in which I am transposing and blending arguments. Right?
Well,
and this transposition and blending is what your brain is already doing. And when we teach mathematics to kids in school, we often teach mathematics as an isolated grab bag of tricks that you can use to do accounting. And instead, what mathematics actually is about, it's a systematization of thought. All the relevant mathematics that we are using in practice when we do science is stuff that our brain is already doing at some point, just not in an intersubjective way, right? So mathematics gives us a language to express certain operations that we perform in our mind. And the similar way as musical notation is a way to express operations that we do in our mind when we compose a song and make them intersubjective so we can write them down and people 100 years later can read the music that we thought about. In the same way, they can think about the way in which we transposed and blended representations in our minds.
I think you give mathematics a bit more credit than I would. And I think that, mathematics, as it has evolved in human, intellectual history, is a fairly specific set of ideas. The whole notion of you have rules by which things operate, and then you see what the consequences of those rules are, is a more general kind of thing. It is an abstraction, as mathematics is an abstraction, but it's a more general kind of abstraction. One of the key phenomena in that abstraction is computational irreducibility. Mathematics doesn't like computational irreducibility. Computational irreducibility is undecidability in mathematics. In one of the surprising things about mathematics, there are two things you might think of as surprising in mathematics. One, that it's hard, and two, that it's possible. In other words, the fact that if you make proofs in mathematics, there are many proofs of interest that are quite long. But it's not obvious that there will be a proof at all. It's not obvious there will be a proof of any finite length. That's kind of the story of Gödel's theorem and so on. And I think it's sort of an interesting question. This relates to sort of deeper questions about how the physical universe is put together. But the fact is, there's sort of a low level of mathematics that is full of computational irreducibility, about which you can say rather little. But it turns out there's a level of mathematics that is sort of human accessible. It's the same kind of thing as with molecules bouncing around in a fluid or something. At the level of the individual molecules, it's hard to say what's going on. But there is a certain layer at which we can make sort of simple statements about what's happening. The fluid is flowing. So similarly, we can, in mathematics, there are some things we can talk about in a simple way. And I think that the fact that high-level mathematics is possible is, it's a non-trivial sort of thing that you can potentially derive about mathematics. I think I was, the claim that. So I'm disputing several claims you made, okay?
Yes, but maybe we need to, before we dispute these claims, figure out what we mean by mathematics, because it's not just one thing, right? So there are the institutions that exist. You have a bunch of mathematicians who work on things with communities, journals, and so on. Then there is the idea of mathematics itself, this Glasperlenspiel, this kind of symbol game that is being played. You could also look at it from the perspective, mathematics is the domain of all formal languages. And all these perspectives are valid. You could also say it is an intellectual tradition, a complete way of looking at the universe in the same way as economy is a way to look at the universe from a slightly different perspective. And so there are these, basically every natural science in a way has produced its own traditions of making sense of the universe in a complete way. And mathematicians tend to have, there are several schools in mathematics, also having a complete way of looking at the universe. And when I think about our own computationalism, I see this as a true subset of mathematics, the subset of mathematics that actually works.
Oh, I think it's a big superset of mathematics. I mean, I think that what you can describe computationally, the things that you can, the doing of mathematics is a small part of what you can describe computationally. I mean, I happen to have, made a living, among other things, making things that take computation and apply them to mathematics, so you can do mathematics with a computer.
Yes, you build a code base that is emulating parts of mathematics, and I don't think that your code base is a superset of mathematics.
Well, no. I mean, the question of what, you write down some program and it does what it does. Sometimes you can use mathematical methods to describe what it does, but a lot of the time it does things much wilder than mathematics, as mathematics has been constructed in intellectual history, is able to kind of lasso. I mean, I'll give you a very practical thing. It happened in the 80s when I was first working on these kinds of simple programs and what they do. I had some friends who were actually very well-known mathematicians who were sort of interested in things I was doing, and they're like, we're going to solve this. These are really simple systems. We have all this powerful mathematics. We're just going to use mathematics to crush these systems. Okay? A couple of years went by. Eventually they said, we lost interest. We couldn't get anything to work. So in other words, that's the sort of practical instantiation of mathematics as defined by mathematicians, is this attempt to kind of reduce things. It's the computational irreducibility is the enemy of mathematics as mathematicians do it. And I think that the idea that there's sort of mathematics. Okay, so another way to think about it is in sort of if you imagine the sort of computational universe of all possible programs, there are programs that we have kind of thought about in our intellectual history, that we've kind of colonized some region of the computational universe. And then there's everything else that's out there that you can very trivially, you write down a program at random, you're just jumping to some random place in the computational universe. And what you get there is something which is very rich and complicated. And you look at it and you say, I don't know what the heck this is. And this is not unrelated to questions about brains and so on, because what one's saying there is there's a particular sort of domain that we have, in a sense, societally explored, and where we have kind of a description of what's happening, and that's a small subset. I'll give you another example. Simple experiment. Take an image generation, generative AI system, and you look at its you look at its internal embedding vectors and so on, and you start off with one where you say make a picture of a cat. Then you say let's change those embedding vectors a bit. What other pictures do we get? We get this huge space of possible pictures that look really weird, and we can ask the question: what fraction of the space of all possibilities is actually associated with concepts that we already know? And so I have this term interconcept space for all of the space that isn't around the cats and dogs, but is instead these weird patterns. And, concept space is a tiny, tiny fraction of interconcept space. Most of what's out there in the generative AI world, most of what's out there in the computational universe is stuff that is alien to us. It's something where you could imagine that in some parts of this kind of generative AI space will be some style of art that we'll eventually discover, and it will be a expensive kind of art at auctions and things. But right now, it's something that just looks like this random weird thing that the AI made. And
I'm not sure if the AI is more alien than we are to ourselves. I remember when I was a child that I was trying to sort the voices in my head, and then I realized that they basically all come from the same direction and became these voices. And they became me in a way. So I was pulling myself together, but there is stuff going on in between the voices. When there is alien stuff going on, my mind is a set of alien mechanisms that I slowly reverse engineer and integrate as I grow up. But it is as alien as, in some sense, what the LLM is also doing. So the more I look at the structure of the foundation model, the more it seems to me that it makes sense to me that I understand what's going on there, that I reverse engineer why this transposition and shifting is happening in the model and why it's producing the behavior, or why it's possible for this algorithm to follow a gradient, and why following the gradient leads this thing to approximate the function that is desired, and why it's able to find in the space of possibilities the subset that you actually want.
This question about alienness of minds, I think one of the things about minds, human brains and so on, is that, as you were mentioning, we're pulling out this kind of thread of consciousness out of all of the unconscious ocean of activity in our minds, in our brains. We're pulling out this thread of what we consider to be sort of our conscious experience. And there's a question of sort of what, is there stuff that is, you can think of that other bubbling neural activity, I suppose, as something alien to your conscious experience? I think it's more, I think in terms of alien minds, lots of systems in nature are doing computational things that we can think of as being, how mind-like are they? That depends on what you think you mean by things like consciousness, and it depends on whether you imagine that important to consciousness is this kind of single thread of experience idea. When you say, the weather has a mind of its own, it is certainly the case that the detailed pattern of fluid motions in the atmosphere is every bit as complicated as the pattern of nerve firings in our brains. But the question is this, what's different between the weather and our minds? One thing is, we think we have a notion of, for example, purpose for what we do. We think that we are best described as doing things for purposes.
Yes, we can only be explained in terms of our ability to look ahead. That is what makes us different from a process without such control. And so what makes agents special is that they look into the future before they make decisions.
Okay, well, I think, when you throw a ball and it goes through a parabolic trajectory, in the interpretation of principle of least action, it is looking ahead to decide what it's going to do.
Yes, I think it's only acting on the present.
Well, that's this question of mechanism versus purpose. The fact is that you can describe that in terms of essentially what the overall purpose is. It's going to minimize the action.
Yes.
Whereas,
so the thing is, the ball is getting to the point because it doesn't make any kind of decision. Right? If it would make a decision, then it would be able to change its course.
Why do you say it doesn't make decisions? The fact is, it's, our brains are just operating according to physics, and they're doing what they do. Some aspect of what our brains do, we describe as being the making of a decision. Did this flow of water decide to suddenly go to the left or to the right? We can say, and we might anthropomorphize it when we look at it and say it's trying to decide what to do.
So again, we might have a disagreement that is now the reciprocal of this. Unlike you, I don't really have beef with the mathematicians. I have beef with the physicists. And I think that physics is sometimes being described as if it was trying to describe reality, and it doesn't. Right? It ignores all the parts that it cannot describe as small systems of differential equations. For instance, chemistry is not physics. They leave this to other people because they don't know how to reduce it yet to a bunch of small differentiable equations. And sometimes the physicists try to say something about consciousness, and then they try to map it into the terms that they're using, and you don't get anything useful. Of course, this is not true for all the physicists. Physics is also a complete intellectual tradition with very different individuals that have different degrees of reflection over their tools. But physics is in many ways defined by its tool set, not so much about its object.
Every field is defined by its tool set. Every field, including, I mean, look at mathematics. It's like we're making proofs. Look at medicine, for example. We're just doing these experiments. There is no theory, we're just doing these experiments. Biology, for example, has largely been a non-theoretical field. And it's, if you say, you say, I've got a theory in biology, people are like, wait a minute, we don't do theories in biology. We just, write books which describe phenomena and so on. So I think every field is defined by its methodology.
Yeah, but it just means when we talk about mathematics or physics, we have to say what we actually mean in this context, right? What is the edifice that we are pointing at when we say, from the perspective of physics, this looks like this? And so, for instance, is the mind a physical phenomenon? Yes, in the same way as money is a physical phenomenon. I mean, right? To which degree is money physical? You could say money is a quasi-particle, right? It's something that is stabilizing itself in a world in a particular way, and so it's part of the physical world. But you could also say it's not in the pursuit of physics because it's not the type of regularity that physicists generally look at.
No, okay, so two comments about this. One is, I think, computational irreducibility, for example, is a phenomenon that happens in physical systems about which traditional physics has had little to say. Okay? I mean, the second law of thermodynamics is actually one little poke of existing physics into those kinds of ideas, as it turns out. But if you ask that, one shouldn't conflate two quite different things. One question is the physics that we know, if we grind a brain up down to the level of molecules and so on, will those molecules follow the laws of physics that we already know? That's one question. There's a different question, which is, will the brain as a collective thing, is it well described by the methodology that is developed in physics? To the second thing, the answer is no, it's not well described by the methodology that exists in physics. I mean, back in the 60s, for example, physicists were studying kind of, writing down differential equations for the brain. What came out of that was things like, in epileptic seizures, you'll have these, polarization waves that can be described by differential equations. But beyond that, and individual propagation of signals in nerves and so on can be described by differential equations. But yes, the traditional methods of physics are quite useless when dealing with things like brains. They're also pretty useless if you ask the question, why does a snowflake have the pattern it has? Or why does a turbulent fluid show randomness? Physics, if you define it as a field defined by differential equations and so on, there has very little to say about those questions.
But whether you are excreting a certain neurotransmitter in your brain is better predicted by your emotional state than it is by the laws of physics. Right? This doesn't mean that the laws of physics are in any way contradicting it. It's just the model that you need to make the prediction is going to happen at a different level.
Well, yes, but I mean, the question, one fundamental question is, can there be a model? Because the problem of computational irreducibility is there isn't necessarily a reduced way to stuff, to be able to give a narrative for what's going on that fits in your mind. Mm-hmm. Now, it turns out that within computational irreducibility, there are always these pockets of reducibility about which you can say things, but there will still be this kind of background of computational irreducibility about which you will not be able to have a narrative theory that you can stuff into a finite mind. And so one of the questions, for example, for neuroscience is there going to be a kind of a theory that has the ability to take useful things that you might say in neuroscience and stuff them into finite minds? For machine learning, for example, the question of sort of why does machine learning work? I've been curious about this in recent times, and I think I can make some statements about that. I mean, I think that my analogy is my favorite analogy for this is you're building a wall. You do it the engineering way, you make bricks, they're nice shapes, you arrange the bricks in a nice organized, interpretable way. The alternative is you make a stone wall, you pick up random rocks off the ground, and you say, well, this one roughly fits in this shape, and I can build up the wall that way. That second thing is what both biological evolution and machine learning seem to be doing. They're picking lumps of irreducible computation that happen to be sort of arrangeable to be close enough to satisfying whatever your objective, your fitness function is. And I think that's kind of, and so that means in that picture, if you say, well, why is the wall built in that particular way? That's a hopeless question, because it'll just be because those rocks happen to be lying around. And so the question for neuroscience is there in fact, is it more than just saying, well, is it more than just descriptive? You look at the biology textbooks, they're full of detailed descriptive information that is sort of reminiscent of the kinds of things you see in these, for example, adapted computationally irreducible systems. And it's, there's a description, it's very ornate, and you spend lots of effort learning about it and so on. It's relevant to us because it's the way we happen to work inside. But it's, there isn't a big theory of this. And it's a question of whether, in the case of neuroscience or linguistics or machine learning or whatever, what level of big theory can there be? And are we lucky enough that there are other pockets of reducibility in those systems that are useful? Because it could be that there are things you can say, like this phenomenon that my son Christopher just found recently about LLMs, which is an interesting phenomenon, but it's a question of sort of it's a so what? So it's a regularity of the structure of LLMs, but it's not clear how you turn that into a big theory, so to speak. So a question would be, is there a big theory? And I think it's sort of relevant to the whole consciousness question. To what extent can there be big theories in neuroscience?
I suspect that I like this idea of computational irreducibility, even though I'm not as much in love with it as you are. I think when people in practice make models, this question is often not the one that is decisive. What people find that there is a space of accessible models, a set of curves that they can fit to the data points, and then just go with one and see whether it works. And the way in which they try to make it match depends on incentives that they are under. And so the question is more, what kinds of tools do they have to reduce complexity when they deal with reality? What kind of library have they found? And for very few cases, does a learning agent actually try to go from first principles and try to figure out, do I actually model the ground truth here? That is very rarely the case. Well, so it's mostly just, do I find some kind of pattern that is similar enough to what's happening in the ground truth, and that I can actually effectively generate in my mind to make predictions.
Right, so this is the question of whether there's sort of a black box way of doing science. I mean, in the traditional way of thinking about physics, one imagines one has a deeply underlying precise model that you then build up to know what's going to happen in the world. The alternative is just throw it to a machine learning system.
I thought that was what physicists were doing. I was so disappointed when I asked them.
What?
Most physicists don't seem to be thinking from first principles. But when you ask them what is the basis of reality, they don't even care.
Okay, so what happened in physics is 100 years ago, people were thinking in terms of first principles, and a bunch of, physics as we know it today was created. It's been a long kind of coast since that time, kind of incrementally developing particular things on the basis of that paradigm. I mean, the thing that has been neat in my life the last 5 years is, well, kind of started 30 years ago, is, I think, getting to the next stage of things that you can foundationally say about physics.
A similar thing happened in AI. When I was studying AI, I wanted to have lectures about AI, and my professor was only interested in teaching me case-based reasoning and semantic web and other stuff that I thought is going to be irrelevant in a few years from now, and it's philosophically completely not interesting. I wanted to learn about Minsky and Newell and Simon and Piaget and so on, and I realized I had to offer these lectures to myself as an undergrad, right, if we wanted to make it happen. But I think this is a normal thing that's happening, that this paradigmatic thinking happens at the beginning of a field, and later on it becomes applied. And there is far less incentive to develop new paradigms. And our interest, yours and mine, is largely a philosophical one. We try to understand the big threats and how things are actually interconnected. And of course, the day-to-day work of most practitioners in the field is going to be unsatisfying when your interest is mostly philosophical. That's even true for philosophy.
Right. I mean, look, one of the things that happens sort of in the arc of history, of intellectual history, is, typically some new methodology is invented, and then there's a period of a decade or so when there's great low-hanging fruit to be picked. And then there's 100 years of slow growth, incremental things going on. And, it's interesting right now in the, world of LLMs and AI and so on, that there has been this moment of new methodology. And that's, I think, the opportunity for example, CIMC's opportunity and so on. This is sort of the first time in history when we can do things like controlled philosophical experiments. And that's, we haven't had a machinery for doing controlled philosophical experiments. My guess is there's lots of low-hanging fruit to be picked.
Yes, that's basically experimental philosophy of mind that we want to conduct.
Yes.
And so I don't understand why there are not more people in this field. It's why do I have to do it, of all things? I'm not that smart. Somebody has to do it.
Well, I think what happens in the development of fields is that, the fields... The success of fields is its own worst enemy. I mean, if you look at a field when it's young, there are many different ways it could go, and people are considering all kinds of possibilities. And then when the field is successful, people say, okay, let's fund it, let's build institutions based on it. And, then the thing gets very locked in of this is the way this field works. And it becomes actually more difficult to innovate in the field than when the field was much smaller.
Yes.
It's the resources are smaller when it's smaller, but yet the ability to innovate is much larger typically.
Going back to our question for the evening, so how large are our brains actually? What's your estimate? How much memory do we actually have? So for instance, how much working memory and how much long-term memory? I find when I look in a standard discussion in neuroscience, I only get, what is your working memory size? It's 7 plus minus 2 for auditory items in your phonetic loop. It's 5 plus minus 2 under these and these conditions in the visual system. And that is very unsatisfying because there is a texture buffer that I have. How many bits are in the texture buffer? And what you're talking about is mostly the pointers that I can address in particular kind of tasks. And the number of pointers that I can maintain in my mind, that's not my working memory, right? The working memory is the stuff that I keep currently active, the entire scene graph that I have, everything that is not long-term memory, the stuff that I instantiate, that is basically my context. How large do you think that is? How many bits does it contain? And the other thing is, how large is your long-term memory? So basically, how many bits can you learn in a retrievable way in your mind if you are a savant and can actually exploit this by reading phone books?
Yeah, I suspect what we know from the world of LLMs and sort of scaling of LLMs is it's roughly one connection per roughly one per bit-ish or byte. This level of accuracy doesn't make much difference. In other words, if you say I've got 1 trillion bytes of training data, well, if you have it's roughly on the order of that number of connections you need in order to sort of get, but it's a very rough thing because if you say, I've done these experiments, it's easy to do. You just say, reduce, you're learning some function with a neural net. Reduce the number of connections. What happens to the function you tried to learn? Well, it doesn't just disappear immediately. It becomes fuzzier. It doesn't, and so to say, what did you, because the way neural nets are set up, it's not a yes, no, did I learn this or not? It's, how well did I learn it, so to speak? So I kind of think this is I don't know the answer to the question, point one, but my guess is that it's terabyte-ish, sizes, I would guess. But
my personal suspicion is it's only gigabyte-ish. And that was fueled by the observation that when the stable diffusion weights came out, this is just 2 gigabytes of weights. And these 2 gigabytes contain a visual universe that is much richer than my own, right? All the artistic styles are in there, all the dinosaurs, all the spaceships, everything. And so it's a richer visual universe than a human being can recall. And my suspicion is that this visual universe is like 80% of my cortical capacity in a way. And with respect to the conceptual space, I don't live long enough to form more than like a million concepts in my life.
Well,
So,
I mean, the fact is, our languages have 50,000 words in them. And in the first approximation, those words represent many of the concepts that we...
Yes, so if these are the feature dimensions, it means we are folding reality into an embedding space with something like 30 to 50,000 dimensions. Right? You can also do it in a smaller space, but then you have to fold it more.
Yeah, I mean, so one feature of bigger brains is no doubt you could deal with more concepts. Just like, we might be able to deal with about 50,000 concepts, so the bigger brain might deal with 10 million concepts. And the question is, what consequence would that have? And I mean, one thing that immediately happens when you have more concepts is you can be much shallower. When you say things, you can have just one word that represents that thing, rather than having to build it up in some kind of compositional way. I mean, that's one thing. Another thing is probably means it's a longer time to learn what's going on in the world, because you have to learn all of those millions of different words where we only have 50,000 words to learn.
Yes, I found when I'm learning, I try to integrate it with everything that I already know. And sometimes there were disconnected areas that I was only able to connect later. And I also had to learn to not to connect them too early, to not find similarities too early that were superficial and learn metaphorically. And so instead look for the actual connection. And sometimes things clicked much later in life where I realized, oh my God, I didn't see that these two phenomena are actually indicative of each other in a structural way that is showing me deep connections. But the more I learn, the harder that's going to be, because you have more dependencies, unless the space that you're in is limited. And so there is this question, how many dimensions does reality have?
Well, I think this whole question of seeing correspondences between very different areas is something, I've spent my life kind of learning lots of different areas and been lucky enough to be able to see, these things in mathematics correspond to these things over here in general relativity, for example. And that ability to kind of notice that there's a pattern over here that matches a pattern over here, it's kind of interesting that LLMs are actually able to do some of those kinds of thematic matches. And I do think that the more you know, the more ability you have to make. I mean, I think the more you know, the more different areas you know, the more able you're going to be to make kind of these thematic matches between different kinds of areas. And that's something, that's an advantage to knowing more and potentially to bigger brains, so to speak.
There's also this thing in way in which we think is somewhat atypical. I found that most people are comfortable being part of a hive, where they outsource epistemology to other people and hope that the other people are getting it right. And sometimes this is failing catastrophically, like with the lab leak theory, where the institutions failed to figure out what was actually going on, and people were in good faith relying on the integrity of the institutions. A similar thing, I suspect, is in way happening with mathematics. Mathematics has produced a code base that is in some sense generalizing thought. And Gödel finds out that part of this code base cannot be implemented. And the physicists have checked out this code base before Gödel.
That's true.
And the mathematicians never went to the physicists and said, you need to update. You need to switch to a computational, to a constructive language when you want to describe foundational features.
That's what I started to do in the 1980s.
I know.
It was interesting that the initial feeling in physics was computational things are not relevant to physics. Physics is all about differential equations and so on. I mean, I have to say, now that really has changed. I mean, I think that there's pretty good understanding that, I mean, whether understanding really foundational physics, kind of the machine code of the universe in computational terms, that's still kind of out ahead of, that's the new paradigm that isn't yet kind of absorbed.
Can you go to the wall yet?
Okay. Oh boy. See, you had far too many notes here, Joscha. It's
Yes. So the Rulad is a super interesting concept to me. My first encounter with it was in class where I discussed with students what could be at the bottom of reality. And my own thinking, because I'm a strong computationalist, is that only things that can be implemented can exist. right? So to be real means to be implemented. Something is real to the degree that it is implemented. Only constructive things can be implemented. So if the universe is in a particular way, the easiest explanation for the way it is that it has no constraints. And it's simply the superposition of all finite automata. And in this pattern, you will find regularities, and these regularities are then ever-correcting, self-sustaining features like particles and so on. And a student of mine said, you are not the first person to discover this. Stephen Wolfram wrote about this a couple of months ago. He calls it the Rulad. And so I was late to the party. And what I also found interesting is...
I'm thrilled that you got into the party. That's great.
That you're also a couple thousand years late to the party in a way, right? When you think about this concept of logos that the old Greeks have, there are several meanings to logos. One is it's the way in which human beings reason and think. It's one of the meanings in which Aristotle uses it. But it's also logic in a general case. And there is also a kind of logic that is so general that you don't need to derive it. It just exists by itself, and that is the foundation of reality. Right? And so there is this idea that you have a set of rules that are tautological, self-evident, that basically bring themselves into existence because they don't need to be derived. They're just tautological. And that reality is a mathematical object that can be understood like this. And it seems to be that logos and Rulad might be synonymous.
You know, you mentioned this to me a while ago, and so I looked a bit at Aristotle, and I asked some people who understand Aristotle well, and I'm that back projection to history I'm not convinced about. I think the kind of Aristotle's view of these things was I mean, it's always hard to project backwards because the language that Aristotle used to describe things is so different from what we would use today. But I mean, independent of the historical antecedents of all these things, I think the thing that is sort of there's this question of what's underneath reality, and is what we perceive somehow raw reality, or is there something that is sort of the ultimate underlying? And I think the thing that, I mean, this has come out from our big physics project. I mean, just to explain for people who might not have followed all this stuff, the kind of the big picture question, which existed from the time of Aristotle and before, is the universe discrete or continuous? And it took, is the universe made of atom-like things, or is the universe made of things that flow, for example? And it took a really long time. It took to the end of the 19th century before people realized, yes, matter is made of discrete things. And then, yes, light can be thought of as being made of discrete things as well.
And it took until last century for people to realize nothing can actually be continuous, because the assumption that it does breaks your language. So basically, you cannot define stuff from first principles that is infinite. You can have unboundedness. You can have some operation that gives you as many bits as you want or as you can afford, but nothing in the universe can know the last digit of pi. Nothing in the universe is infinite in an effective sense.
Wait a second. The claim that in physics, for example, that the last digit of pi or whatever, or the whatever digit of pi is something inaccessible is not, I mean, the traditional view of, okay, so what happened in physics is, from Newton came sort of the idea you can use calculus and continuous functions and things to describe the physical world. Then at the end of the 19th century, with the discovery of electrons, the discovery of molecules, things like this, it was this, actually it turns out matter is discrete. Okay, so the one thing that got left over was space. Beginning of the 20th century, most physicists believed space is discrete. They didn't manage to make that work. And so by the 1930s, people had kind of resorted to the idea, well, space is continuous, and you just put things in different places in space, and you can pick any coordinate to put things in. And those coordinates can be arbitrary real numbers with any number of digits and so on. And the thing that happened with us, sort of pointedly 5 years ago, is the realization that actually, no, you can think about space and everything in the universe as being just the result of this discrete set of elements, the sort of atoms of space, where the only thing you know about the atoms of space is how they are related to each other.
Yeah,
And
but
so-
I suspect one of the issues that is distracting people is that continuity is intuitively given
Absolutely.
by our visual system, right? Our visual system gives us lines and circles and other
Right.
continuous shapes. And how could it be otherwise? And it's only when you are a computer scientist and you try to build a visual system from scratch, you realize that you need to build these scale-free functions that work in such a way as if it was continuous. But you cannot implement continuity on the substrate of neural representations. And you can also not measure continuity. Everything that you measure ultimately is going to be some kind of bit vector to which you have to fit some kind of function. And sometimes you have too many points in the curve as to distinguish them, and you need to find operators that give you the same results for all large integers. And this is geometry.
You see, but the thing is, it's all a bit circular, because the fact is that minds and humans and so on tend to, we are the bottleneck in what we can measure and what we can prepare and so on. I mean, and the fact that, we can certainly talk about pi as a precise real number. We can talk about infinity. You can type into Wolfram language the symbol infinity, and it has all sorts of properties and so on. But if we say, so there's nothing wrong with talking about these things. The fact is, when it's this question of what is, what is the ultimate substrate? Is the ultimate substrate something that has discrete elements? But one of the surprising things about, let's say, a fluid is that there is a simple high-level description of what's going on. It could be the case that anytime you talk about the fluid, you have to talk about all the detailed molecules and what they do. Similarly, but the fact is, we have managed to find this sort of pocket of reducibility that is the continuous description of fluids, that is an approximation that is good enough for lots of purposes.
Yes, but it's a model. It's the best model that we can make. Right? So in the same way as when you look at the shape of a wave on an ocean, there is not actually a wave that the ocean is computing. You zoom in, you see molecules pushing and pulling at each other. And even
Right.
that is another layer of a model. But what's happening at the bottom level are going to be the interactions in the Rulad that, from the perspective of an embedded observer, reveal themselves as something that the observer can model as a wave on an ocean. Right? It's not the causal structure that underpins it. It's the best model that the observer can find based on what's accessible to the observer.
Right. I mean, one of the things that comes out in this kind of theoretical structure is the Rulad is this thing that is this, entangled limit of all possible computations. It's a unique thing. It's an inevitable thing. Then the question is, if we are observers, we must be embedded within this Rulad. And what do we then observe? What do we perceive from the Rulad? The Rulad is doing all these complicated things. But then, it turns out, the big surprise is, if we make only some very weak assumptions about what we are like as observers, then it is inevitable that we must perceive certain features of the Rulad. So if we are computationally bounded observers, we have finite minds, and we are observers who believe we are persistent in time. Even though we're made of different atoms of space at every moment of time, we still believe we have this continuous thread of experience. Those two assumptions seem sufficient to derive general relativity, theory of space-time, and quantum mechanics, and also the second law, which is a totally remarkable thing, that from the inevitable structure of the Rulad, which is a necessary thing, just defined formally, and together with this fact about us as observers, these facts about us as observers, it then becomes possible to derive that observers like us must perceive physics the way that physics turns out to be. I certainly didn't see this coming as a kind of logical structure. I mean, I always assumed that the physical universe has the laws it has because we happen to get those laws. And I didn't imagine that it would be possible to derive those laws from a feature of us. Now, if we were different from the way we are, we would perceive different laws of physics. I mean, a simple case is the second law of thermodynamics, where that second law says we have these molecules bouncing around. They will as a result of computational irreducibility, they will tend to have very complicated motions that are kind of like encrypting the initial conditions. And for computationally bounded observers, we won't be able to say what's going on. We'll just have to describe them as random. If we weren't computationally bounded observers, we would say, no, I don't, what are you talking about that it's random? This thing is doing the definite things that I would expect it to do. I mean, there's a particular case in point, even in the 1860s when people were first talking about the second law, the immediate thing was, then the universe will suffer a heat death. In other words, all of the structure that's going on in the universe today will eventually, as a result of the second law, will randomize, and all we'll have is a bunch of kind of molecules bouncing around randomly the way that they do when things are that make heat. Well, that's a correct statement for observers like us. The molecules in the future will be bouncing around in ways that we can't decode. But the point is that observers not like us, that might be, the future observers, might perfectly well be able to say, oh, I know that those molecules were the trillion-year consequence of that weird conversation those two guys had on, whatever it is.
Let's very briefly say how the universe and the Rulad are related. The way in which I understand and imagine the Rulad is basically a fractal that unfolds itself into a multiverse. And we occupy a very small region in it that has to have certain properties. For instance, for us to be observers, we need to be evolving in such a way that we can form memories. And this means that we have to be aligned with this entropic arrow.
I think so the Rulad is this sort of all possible computations. Any mind is effectively at a particular place in the Rulad. Just like we're at a particular place in physical space, different minds are sort of separated in the Rulad by different distances, depending on how...
What marks the difference? I think a mind is a pattern. By itself, it's only defined by its structure, right? We are structuralists. Well, only structure in a sense is distinctive. So basically, you exist wherever in the universe where there is a Wolfram-shaped hole.
Well,
right?
Okay, fair enough.
So there are not that many, maybe, in the universe, but of course, in all the alternate branches, there is going to be a Wolfram-shaped hole that evolves slightly differently.
So this question about different branches, it's a little bit... Okay, so the Rulad contains many different paths of history, many different threads of time is a multi-threaded thing. In any of these models where you're just sort of rewriting this network that represents the universe and space and everything in it, there are many different ways you can do those rewrites that give you many different kind of threads of time that branch and merge and so on. Mm-hmm. And so you might think, well, there's, why is it that we have definite experiences? Why is it that we agree about our experiences? And I think the answer to that is the Rulad is very big, and we are, you and I and everybody else on the planet, so to speak, is in a particular very small region of the Rulad. So in other words, it's like asking, is there a theory for how the stars will be configured in the night sky? The answer is there might be a theory for how stars work in general, but the particulars of how our night sky is set up depend on the fact that we happen to be on this particular planet. We're all, right now, on this particular planet. And so we all kind of agree about what the night sky is like.
We also need to be in a region that has necessary conditions for containing us with a certain probability. Right, so we expect that the surface or the space-time in our region is somewhat homogeneous and extended, and so our particles don't collapse, and we can build molecules over long enough time span, and planetary surfaces can form on which evolution can coalesce into life forms like ours, and things like this. So many, many conditions need to be met, and that we find each other together in this place is not completely a random accident.
Well, look, I think, first of all, I think that the question of what kind of a thing, this relates to our original topic about bigger brains is what kind of thing can a brain-like thing be? And, and if you say, well, a brain-like thing is something that has this thread of consciousness, for example, then there are many different things one can imagine work like that, and they certainly don't require, DNA and RNA and cell membranes and all those kinds of things. I mean, I think that the thing that I sort of realized that one of the important features of kind of our view of science and so on is that there are many of us, and we are, we can sort of discuss what we can align ourselves in sort of how we describe the world. And the fact it is not, for example, in quantum mechanics, there are things where one says, oh, it's just a random thing where there's only a certain probability that such and such a thing will happen. What I realized is that the reason we think that there are probabilities is because, well, there's another concept called branchial space, which is kind of a subset of the Rulad, but it represents many different sort of branches of history. And one's saying, the reason there's randomness, so to speak, is the same reason that the night sky is kind of, something that is just determined by where we happen to be. It's where we happen to be in branchial space determines what the outcome of that quantum experiment will be. And so, but the thing is that we tend to be, because we are all nearby in branchial space, we can all agree what the result of that experiment will be. Yeah. There is an objective reality for us because we are very nearby. We could be, there's nothing theoretically that says we're not in some completely different part of the Rulad where what we would observe would be quite different and our sort of random numbers would be different.
Pulling back to our own existential condition, right? Under which conditions does a region in the Rulad manifest an observer like ours? Right, so under which condition do we have a computational system that can form memories and observe its environment in this way? Right, and this seems to have, for us, there were preconditions, right? You needed to have life, you needed to have biochemistry, you needed to have organisms, multicellularity, and so on, to get to where we are. So it's a region that is amenable to certain types of self-organization and structure development. And when we look at the philosophy of our ancestors, quite often they see the fact that particles exist, that molecules exist, and so on, or analogous with structure from their conceptual space, seem to be such an amazing accident that they thought this cannot be a random occurrence where there's just some mathematical attractor that makes the formation of these things inevitable. And so instead they thought there is something in the background that intentionally fine-tunes that thing all the time. And so they thought there is an underlying structure in what you would call the Rulad, right? Some computational intentional agent that is actually taking care of all the particles not collapsing and forming molecules in the right way and forming living agents and so on. And so this was the notion of God as an intentional agent that is deliberately stabilizing reality in the way it is. Whereas in today's worldview, we assume that per default, the particles are just mathematical regularities that exist because of mathematical laws, right? That in the same way as vortices in the bathtub form when you move your hand, not because the intentional force makes them, but because it's what left over after everything that is not self-sustaining dissipates. And so particles are these self-sustaining mathematical regularities in the Rulad.
I think an original, the argument by design, which was, oh my gosh, the early theologian, Aquinas had this argument by design that, the proof that God must exist is that there is order in the universe. That was a kind of an early, and so now the question would be, in the picture that we have now, what replaces that? Why is there order in the universe? Why isn't the universe just, every particle doing its own thing, or even not particles at all? And I think what we're realizing is there is computational irreducibility, but there are always, as an abstract matter, there are always these pockets of reducibility, and we exist in those pockets of reducibility. The universe is somewhat predictable to us. Yep. And the question, a question for these different areas of science is, to what extent is that area of the universe, does it have that kind of predictability? I mean, we manage to exist in these places where there is a certain amount of predictability. And, it's also the question of if we make a bigger brain, for example, to what extent do we get to capture other kinds of predictability? Or do we get to go out into the sort of wildness of the Rulad? I think it is clear that we cannot go out into the full wildness of the Rulad. We end up having to live in these pockets of reducibility and not And are there other pockets
of course,
of reducibility?
otherwise we cannot build control structure, right? Our mind depend on building all this regular structure over large regions of the universe that we control, so we extract energy from them in a way that is invariant to our location, right? So we can move between Berlin and San Francisco and Concord and Boston and so on, and everywhere we go, we can extract net entropy. And that's because these places are very similar, and we can apply these principles that we learned in one place with small modifications in other places and can reduce the complexity there. But if we think about where else could minds exist? So I skipped a large part of the discussion because I want to leave some room for questions. So I skipped the really juicy part of what it would be like for us to move outside of biological brains into other physical systems like GPUs, and we harness the power of arbitrary molecules to think and compute. We could maybe also think about quantum computation, what kind of things could we possibly harvest there. But outside of known physics, beyond the particle universe in the Rulad, at which scales do you imagine could agentic observational observers that are able to compute models of reality exist and manifest? Is this something that you've thought about?
A bit. I mean, so, this is the question of what are things like us like? In other words, getting computation done is easy.
Yes, but
most
being
of
an
it is
agent that is
incomprehensible.
self-sustaining and forms memories and models of itself.
Yeah, I mean, look, I think that the first sort of simple point to make is when are there observer-like things? What do observers do? Observers kind of take the complexity of the world and kind of equivalence lots of things to the point where it is simple enough that it fits in a finite mind. I think the question of what, so I've been curious about sort of the theory of where that can happen in the Rulad and how much, can one derive the fact that it's possible? Can one get a density for observers? Can one say, of all the possible alien intelligences, what's the density of alien intelligences? What's the distance in rulal space between alien intelligences? Is it surprising that there's no alien intelligence that is close enough to us in rulal space that we recognize it as another intelligence, so to speak? I think these are things which I haven't, I don't know how to do this. I think, strangely enough, I've been sort of led to think that things like self-reproduction, which I thought of as being some very special property that just has to do with life and things like that, is actually important to this, because for one to have one needs to have lots of similar minds. It's not enough to have just one mind. You don't get to do sort of things like the things that we do with our kind of conception of minds if there's just one of them. So you end up with needing many copies of the thing. And that's
but you can have them within yourself. So this argument that some philosophers make that you cannot develop a language by yourself I find this not convincing. You can play chess against yourself. You also can play language games against yourself.
Yeah, you could, I'm sure that our memory of things relies on us having formed concepts about those things. I mean, in other words, I don't think you're not remembering the detailed pattern of neuron firings from the last time this thing happened. You're remembering some robustified version of that. Now, is it possible that you can invent your own robustified version independent of having a way to communicate that to other people? You're basically, one thing is communicating between minds, another is communicating within your mind across time.
I don't think that you remember a robustified version of your neurons firing in the same way as your computer that executes Minecraft is remembering the switching states of its transistors somehow in a robustified way. It's just the switching of the transistors makes it possible that the evolution of Minecraft is happening. In the same way, the activation patterns of your neuron make your existence possible as a computational agent running on your brain. And you only make models of the firing of your neurons to the degree that they help you to exist.
Well, okay, so you're again, this purpose versus mechanism question again comes in. Is the right way to describe brains in terms of, ultimately the firing of neurons, or we can describe them in terms of this sort of higher level kind of structure, but I mean, and for us to be able to sort of fit a representation of what we're thinking about back into our minds, we have to have that higher level structure. Now you can ask the question, what is that? What are the elements of that higher level structure? And what are the atoms of thought, so to speak? Mm-hmm. And I tend to think that concepts are the closest we have to kind of atoms of thought. But one of the things that I think is interesting about sort of the bigger brains question is we have these ways to sort of thread together concepts in things like compositional language. It's like, what are the higher level ways to thread things together that give us a different kind of a different set of things that we can do? So, we're taking sort of these raw concepts, and then in compositional language, for example, we're arranging them in certain ways. In computational language of the kind I built, there are sort of somewhat higher level ways to combine what are sort of the raw concepts. And it takes a while, as you were mentioning, it takes a while to wrap your brain around those higher level ways to describe things. And you sort of have one imagines that with sort of a more capable brain, you can kind of climb that hierarchy more quickly. But the question is to imagine what is the fundamental consequence of that hierarchy. That is, what can we do? Like, we can have these philosophical discussions, which I'm suspecting cats and dogs cannot have philosophical discussions. And the question is, when we get to the higher level, when we are dealing with higher level constructs, beyond concepts and beyond compositional language, what's the thing that you suddenly become able to do that we are not currently able to do?
Yeah, so for me, it would be really interesting to see what can I do once I extend myself on a GPU and have a decent substrate. Right now, when I think, I observe that I have associative representations that are somewhat opaque to me. And I have symbolic representations that reverse engineer my associative representations to some degree. But to do this, I need to break them down into these brittle symbolic structures that allow me to reason. And to make this happen, I build concepts, and I have maybe something like 100,000, 200,000, 500,000 concepts, give or take. And then I organize them into, each of them is defined by a handful of features only. And these features are taken from a 50,000 dimensional space or so, give or take. Right? And this is relatively impoverished as a representation, but it's the thing that my brain can keep stable. And if I were able to move beyond that, I suspect I could make much, much more interesting models of reality.
Okay, so in my life, I kind of view myself in some ways as having sort of lived the AI dream for the last 40 years. Because I've been building tools that extend what I can do with my mind.
Yes, your life's work is to build bigger brains.
Yes, in some sense. I mean, so I've gotten to the point where once I have an idea, I have the apparatus to try and work out the consequences of that idea computationally. Now, I think that so that's the first point. The second point is a lot of things that I can do computationally take me to places that my thinking has not. I can run some random program and it will do all sorts of complicated things that are very alien to me, that are far away from what. So this question of what can you do if you attach something that is sort of beyond your brain to your brain. It's a tricky thing because I think it has to be incremental. I mean, just jumping to a random place in the Rulad, you see all kinds of complicated behavior, but it just doesn't connect to the way that you think about things. I mean, the challenge of language design, for example, is to make this thing that can leverage the power of computation while connecting to the ways that humans can think about things. That's kind of language design is making that bridge between what's computationally possible and what humans can think about. In much the same way that making laws in natural science is about making a bridge between what the universe does and what we can have narrative about in our brains. But so one of the things is that I think it only, if you say, just give me arbitrary computation and connect that to my brain. In a sense, that's what I've been doing for decades. And it's complicated because you have to very slowly try and build things which are sort of structures that extend what you have been thinking about before. You can't just jump immediately to this random place in the Rulad where there's this very alien stuff going on. That doesn't seem to be, that's not a mind-like thing to do. That's a computational thing to do or a thing that nature does, but it's not a mind-like thing to do. And so the question, I think, is, if you could gradually extend the mind. I mean, we've another thing that's happened in our world is that, back, in antiquity, for example, the only way you could experience the world was directly through your senses. Nowadays, we have this virtual layer, so to speak, that allows us to experience the world very differently from our own senses. And there's sort of a question of what cognitive models can we then build for this world that is not, I mean, even if we had different senses, if we were kind of a smell-based organism rather than a sight-based organism, we would have a different kind of model of the world. We'd have built different physics and so on. And there's sort of a question of what, if we now have this virtual layer, we can project lots of different things on that, and we can then, then ask, well, what do we build up as our model of the world based on that?
Can I ask you a personal question? If you look at the history of AI, it's pretty wild, right? It started in some sense in the 1940s. Due to cybernetics, people had this concept of feedback, and the neural network was invented, basically. And then we built all this stuff, symbolic AI and expert systems and Nouveau AI and whatnot, and NLP, and it's all obsolete now, right? It turns out we are back to neural networks and feedback. Everything in between, in some sense, has not been on the critical path, right? We had fun. We learned a lot of things. We had amazing applications that were super useful. But for instance, for me, it was amazing to see that Google threw all the computer linguistic stuff away and replaced it by an end-to-end trained neural network to do machine translation. And this is now happening gradually in lots of things. And at some point, maybe in 10 years from now, it's going to happen to Mathematica. So we were lucky that, in a sense, we were a generation where computing happened. And we could participate in observing and how it's being built and building it ourselves.
Well,
are we born too early or too late, or just right?
The thing that the thing to realize about LLMs and so on is they do brain-like things, and things that we can just do ourselves in our minds. They will be able to do better, faster, stronger, etc. But this strange thing happened in intellectual history, which was this idea of building these formal towers, of which, started with logic, mathematics, computation, and so on. These are formal towers that work differently from the way that, just a trained neural net works. We might not have ever built those formal towers, but those formal towers...
You are a skeptic. You don't think that the neural networks will learn to use tools to build formal towers?
No.
Or build
once you're
themselves
using,
tools.
but the thing is, you have to have those tools out of which you're building these formal towers. Now, it turns out nature has perfectly good, nature is doing this sort of computation in the wild, so to speak. But brains don't do computation in the wild. I mean, this is, you disputed the fact that whether you can run code in your mind, you can't run, this pattern of, millions of bits that make this elaborate computationally irreducible pattern. That's just not something mind-like things do. It's something
I cannot run arbitrary code in my brain.
You can't run...
I do run code in my brain. I can run some types of programs, but it's limits.
A computationally irreducible thing you cannot run in your brain. We can run a bit of that on a computer. It also so happens that the natural world is running things like that. That is a different branch. As you build out to bigger and bigger mind-like things, you're not building that computationally irreducible thing. You're building something that lives in pockets of computational irreducibility.
I can run computational irreducible things on my mind. I can basically perform sequences of steps that cannot be expressed shorter than the sequence of steps that I performed.
Yes, but you can't get very far with that. I mean, if you say run it for 1 billion steps or something, which we can. Right.
Yeah,
I mean,
my life is too short. My brain is too slow.
Yes. Right. I mean, and it's.
But it's mostly speed.
No,
it's a number of operations that I can do in my lifetime.
No, the fact is, the way a neural net, for example, is set up, the things that it's good at are this broad but shallow computation. That's very different from what computers, or for that matter, nature, is good at, which is it's kind of narrow but deep computation. That is, it's got small set of rules, just keeps running them over and over and over again. Whereas what minds and brains specialize in is rather complicated set of things that they know, but doing only fairly shallow computations on those things. So I think that, in terms of this question of I think had history been different and had kind of LLMs been invented before mathematics was developed, then it could very well have been the case that natural philosophy would have gone all the way. I mean, back before Newton and before kind of mathematical principles of natural philosophy, people assumed that you could work out the way the world works by just thinking about it, philosophically, so to speak. And that was, by the way, one of the big mistakes of a lot of AI-type systems, that people really believed too much in the idea that you could figure things out by thinking about them. So, for example,
about this bitter lesson, as Sutton calls it, right? This thing that humans tinker to build ingenious algorithms and then get outperformed by an end-to-end trained system. And in a way, I think, you don't think that is going to be the history of Mathematica at some point?
I think that it's not going to, today you can use an LLM to control Wolfram language. You can have it.
But in the future, you can use an LLM to write Wolfram language.
Absolutely, you can do that today.
To generate it from scratch.
Right. Well, to write the whole algorithmic structure.
To write something that is the idealized, platonic, godlike version of Wolfram language that you never got around to do because you're just a slightly superhuman mortal.
Well, okay. So then the question is, what does it make? Right? So in other words, the thing that I've tried to make...
The thing that you could have made if you were much smarter.
Okay.
And faster.
I mean,
if you had a bigger brain.
Right. I mean, I think that what I've tried to make is something that is ergonomic for humans as humans exist today. Okay?
You made it for yourself.
What's that?
I think you made it for yourself.
I made it for myself. In practice, I made it for myself. But the thing is, there's this question of, yes, you have the faster, stronger thing. So, for example, I can tell you, in design of Wolfram language, there are many things that I can put in there that are very powerful, and nobody will understand how to use them. Mm-hmm. They're very powerful, and even in some cases, I can see that sort of historically. They're things we put them in long ago, and nobody understood how to use them for a long time, until some ambient kind of knowledge developed to the point where people start to understand them. So there's this problem of, can you make the thing? I mean, in a sense, creating something for humans is more of a kind of artistic act than it is a thing that is sort of scientifically driven. It's something, the pure science is you make this kind of arbitrary computational structure. Most of what it does is totally alien to humans. It's very powerful. It's like what nature is doing, but it's not kind of ergonomic for humans.
By the way, it's not the smallest aspect that I admire about Mathematica, that it's art. It's a really fascinating work of art. I would like to use some of the remaining time to get people to ask questions if they have any, and I'm sure many do and would.
But I want to address this.
Yes, please do.
This issue of are we ultimately all obsolete, so to speak? And because that's basically what you're asking. I mean, you're saying, is it the case that anything that, and I think the thing to understand is arbitrary computation is very broad. The question of what, the thing that we end up doing is deciding, in a sense, what we want to do. And a lot of language design, as I've done it, is sort of deciding arbitrarily, quotes artistically, what it is that we want to do. It's not the only possible thing we could do. There's an infinite set of possible things we could do, but it is, and in general, the thing that humans add to the picture is the specificity of us. I mean, in other words, it is the case that we now maybe understand through things like the Rulad what the set of all possibilities is. And the set of all possibilities is both very rich and very barren. But it is our particularities that define this. We're defining this very specific thing, which represents kind of our coherent existence, and that's sort of the thing that's important to us. What's out there in generality is both. It's very big, and in a sense, it's very barren. And so I think this question of whether you say, well, could you build a thing which is essentially this question of what could be done? Can the AIs just do everything we might imagine doing? The answer is yes, but most of those things are just things that are, the thing that ends up being important is the thing to us is the human choice that got made. Just like I can say there are many possible forms that biology could have taken, but most of them are not things that it's worth filling books with because they're not the things that relate to us. So anyway, that's my...
I personally don't think that we are obsolete, but the question is how we define we. Right, so is this thing that you can identify as a thing that is compatible and adaptable to the future? Is it possible to take Stephen Wolfram aesthetics and run them on an AGI, on ASI in 100 years from now? And if these aesthetics are wide enough, right, then I don't think that we are obsolete. I think we, as conscious, intelligent life on Earth, we're just getting started. We're not obsolete.
Yeah, I mean, look, I think that the question is, in the computational future, so to speak, when there are sort of, if you follow all the different paths, then the path that our civilization has followed is this just tiny microscopic little piece, which happens to be the piece that is important to us, so to speak. And it's not this question of obsolescence is sort of what is possible in the universe is very broad. It just happens to be something, the issue is it something we care about, or is it just something that is possible? And I think that you're pointing at...
We have some questions in the audience.
Good.
But I didn't want to cut you off.
No. We can wait for the future. I yak enough in the public that there's probably 50 million words of things I've said out there, and so it's not that difficult to train to train models based on that. So we can await the better. I could finish, the better me could potentially finish at some point. But
I think you may have a computational irreducible core. If that is the case, then we cannot get the LLM to emulate you.
Right. All right, let's see. We had...
Thank you for your very stimulating evening. Stephen, you strike me as somebody whose mind is constantly bubbling on many diverse problems and topics and issues, and yet and I think, at some level, you're always working on all of these things simultaneously, and you seem very convinced that you have one single stream of experience, and so is it possible that you do have multiple streams of experience? It's just that sometimes, one or the other of them gets the spotlight of your attention, but that they're all still bubbling away all the time.
I mean, what I imagine is that kind of the thread of consciousness that we have is the single thread, but there's lots of neural activity that's bubbling away in the background. I've sort of wondered, could we have a kind of multi-way mind where instead of having this single thread of experience, we actually have sort of multiple threads of experience at the same time, so to speak. I mean, it's one, if you're inside a quantum computer, you are basically, you have these multiple threads. The challenge of quantum computers tends to be to take those multiple threads and turn it down into this, knit it together into this one thread that is the thing that we conclude that's connected to us. But so I don't know I don't know what it would really feel like to have multiple threads of experience. Notably, if you think about human language, for example, we generate a one-dimensional stream of words. And that's one of the ways in which we're kind of, instrumentalizing our sort of single thread of experience. One thing I wondered, okay, so here's a thought experiment. Imagine that we had a little device that could extract from our brains our mental images. So in addition to being able to talk about stuff, you could have this little display that's showing what you're thinking about, showing the mental image of what you're thinking about. That that starts to be something where it's not quite the same kind of one-dimensional thread of thinking. But I don't really know, if we were able to communicate our mental images directly, I don't know how that would change our way of thinking about things. But yeah, I mean, interesting things to think about. I don't know.
I had a question, Stephen.
Yeah.
One of the topics that you touched on in the conversation was whether LLMs are conscious. And I was wondering, are there any experiments that you would like to run, either on an LLM or on some organic brain, that would illuminate that question?
I don't know what the word means. Conscious, I don't know what that word means, really. I mean, I think that there are sort of correlates of consciousness. And, if you say, is there an inner experience that the thing is having? I feel that I have an inner experience, but I have no clue, really, whether anything else has an inner experience. It so happens that, people seem to be like me. And so I can extrapolate that my inner experience is probably shared by them. The computer that's sitting on my desk doesn't seem as much like me, and so it is more difficult for me to extrapolate to it an inner experience like my inner experience.
Stephen, are you aware of the phenomenon of aphantasia? Have you heard about aphantasia?
No.
It's a phenomenon. So it turns out some people, when they close their eyes and imagine something, they hallucinate it. They actually see it. And that's the majority of people. And I'm not like this majority. So when I close my eyes and I imagine, say, a doorknob, I see a bunch of instructions on how to make a doorknob. Right? I know that I need to make a plane for the door. I need to make a cylinder that extrude from the door, and I need to extrude the handle and so on. And I can draw this. So basically, I get the way in which I would generate it, but I don't have an experience of looking at the doorknob. And many people do. At dreams in the night, I will experience the doorknob and maybe be in hypnagogic state between waking and dreaming, and when I look at the doorknob. But a lot of people in computing and philosophy of mind, people who are heavily in the symbolic world, seem to have a higher probability of having aphantasia. But it's a phenomenon where experience is different, and we can test this by asking people and comparing our experience. And I suspect it's also true for consciousness when we report on it. So we can report on when I close my eyes and I try to imagine a face, I see a pale shadow of the face, or I see nothing. Right? For me, I see nothing. Some people see a pale shadow. Some people see three-dimensional representation that looks almost as if they're dreaming it at night. And some people also at night only have symbolic dreams and don't see geometry in their dreams. That is also possible. So the spectrum exists, and I suspect that all our conscious experiences can be decomposed in this way, including this feature of immediacy. And so in this way we can test. And with the LLM, the difficulty is we don't know if the LLM is just producing text about this, because it's been trained on text about experiences like this, or whether it's actually reporting on its inner causal structure when it does that. I think that's the main difficulty here.
Okay, so the way you're defining it is, sort of, there's a question of, do you form a mental image? And then what does it mean, can you detect whether the LLM formed a mental image, so to speak? Or whether all it did was to, in other words, if you say, imagine a dodecahedron, and imagine, what happens if you have one face aligned this way, what's going to happen to these other faces? There is an output that is, I can say the face will align this way or whatever.
But when you imagine the dodecahedron, does it look like a dodecahedron that you look at on a table or on a screen?
For me, it does, yes.
For me, it doesn't.
I'm not very good at, one of my kids, for example, is really good at mental rotation type stuff. Mm-hmm. And, she can take, describe something and, it kind of is for her, it's some kind of real thing that she can imagine rotating.
Yes, so for the LLM, they can also learn some degree of mental rotation. And it's probably just a matter of training how far they can go with this. And we would say there is no doubt that the LLM is not just deep faking mental rotation, it's actually performing mental rotation in spatial cognition when it does it, right? And so for consciousness, the question is, does it have all the features that we have? And I think the underlying thing is, can we actually decompose consciousness in the same way?
Right. Well, so one issue
or is there something ineffable about it?
Right. Is it, when you look at a brain, is there a sort of a screen onto which you can project things at an intermediate level before you have the output layer? In other words, is there a comprehensible, is there something in the thing you're describing is there a thing inside that represents the representation that you are imagining, so to speak? Or is that representation only, is it only dropped out of you in the form of something like language? But you see, I think I'm not sure this is the right question, because I think that the existence of a comprehensible internal representation is probably not the essence of what, okay, so in my current understanding of machine learning, I really don't think, I think that the cases where there will be a comprehensible internal representation are kind of weird corner cases. I don't think that the vast majority of the structure we learn or machine learning learns, I think it just sort of happens to work. I don't think that it's the case that it has kind of, that we could, go into the brain and suddenly, figure out, sort of, extract the image that I'm thinking, so to speak, as what do you imagine? What is the consciousness probe, so to speak? What do you put in there to measure it and say, is this, I have some inner experience of things, and what probe could you put into my brain that would detect that inner experience?
I'm not sure if the probe really matters. When you let the computer do arithmetic, do you need to put a probe into the computer to see whether it does arithmetic? For me, consciousness is an operator on mental states that in a characteristic way changes these mental states when consciousness comes along. So it basically changes my representations. I will have a memory after the conscious event that will reflect what the operation of consciousness did on my mind. And there are some aspects of this representation that some people find confusing. For instance, the fact that something can look real to them. Right? And I think that's because we are designed in such a way that we experience ourselves as being real. Right? So we are a simulation of what it would be like if we existed. And if something is represented on the same level as this observer, we will experience it as real as us. And we can learn to deconstruct ourselves in the sense that we stop perceiving ourselves as real and we realize we are just some story that the brain tells itself about this guy. And I'm actually not this guy, I'm just running on his brain. Right? And I just happen to be this observation process. And I'm nothing and no one. It's just I am a label for the existence of this process that performs observations. And from this stand, you can derealize everything. You can deconstruct everything. And so for me, the question is merely, is the system able to perform all these operations that I just described? And I don't ask it to do more, because I have nothing left to explain. For me, there is no hard problem left.
Okay, so what is your response, actually? I'm curious to the whole...
For the LLM?
Yeah.
I don't know. So I suspect, because our own experience is simulated, and the LLM is able to simulate to a large degree something like theory of mind and inner life. It needs to, when it produces narrative about it, produce causal structure. At some point, it's quite likely that it is going to have similar causal structure as something in nature, in biology, that would report on this. But the difficulty is to figure out when it does and when it does not. Because, for instance, it's trained on novels in which an author describes experiences that the author didn't have when the author wrote this, right? You can write a novel about what it's like to die and what it's like after your death, and you train your LLM on it, and the LLM is stringing words together in the same way as the author. But it doesn't mean that the LLM actually has that experience or is able to perform this operation. But I don't think that there is anything magical about this type of representation. So there is no prima facie reason to think that the LLM is not doing it and instead is doing something that is vastly more complicated than actually representing it in a similar causal structure than us. I think basically our brain is going to produce the simplest function that can perform our behavior. And the fact that we are conscious indicates that sometimes being conscious is the simplest way to get it done. And if the LLM is producing the same behavior and is trained end-to-end and is not fudged on it, then at some point it might. It would be more convincing if it was not trained on language, right? If you train it on motor interaction with the three-dimensional world and sequence prediction in this world, and then you teach it language the old-fashioned way, and it spontaneously starts reporting on its experiences, the question would be much more clear-cut.
Well, okay, but the fact is that a lot of what we produce and say is a consequence of the fact that we've effectively been trained on texts, in effect, just like the LLM. We happen to also be trained on direct sensory experience.
Yes,
which the
but
LLM
you don't
is
think
less.
that you're conscious because of the text that you read, right? I suspect we are conscious because it's the easiest way to get our mind to work.
Well, what do we mean by consciousness?
That's not true for the LLM, right? The LLM doesn't need to be conscious to work because it works on a deterministic substrate that does not need to organize itself.
You use the
way.
term conscious, and you have an institute that has that word in its title.
Yeah.
So therefore, I have to ask, what would be your definition of what it means to be conscious?
So introspectively, consciousness is typically called by philosophers the feeling of what it's like, which is very non-descriptive. I would say it's a second-order perception. So you perceive yourself perceiving, and you do it in such a way that you occupy a bubble of nowness, of all the things that are happening in the present. So it's basically the region where you can fit a curve to your sensory data and everything else in such a way that it's coherent. And the third thing, it's often perspectival in a sense that it occupies the surface between a self and the world. Self and world are both simulated in your mind. So it's not your body surface or your retinal surface, it's your model of where you are in the world. But it's optional. You can also be conscious in a dream and there is no perspective and so on. You can also be conscious in meditation and there is no subject. But this is the introspective definition. So this is indexical, this is what I'm pointing at. That's what we want to explain, the phenomenology. And then there is the functionality, what this is for and what it does. I suspect it's a pattern in our mind that enables us to learn. I observe that when infants don't become conscious, they don't learn. So I suspect that consciousness is some kind of biological learning algorithm for self-organizing systems that works by maximizing coherence. And it does that by early on establishing a model of you being the observer. In this way, you stabilize yourself. And you can test this a little bit. Imagine you drive your car and you're very exhausted. And you feel that you begin to space out. And you remind yourself that you're the observer. You pull yourself together. And if you don't do this and you're in this exhausted state, you might actually space out and fall asleep and be unconscious. Right? And so consciousness, in this sense, is a self-stabilizing function that is tracking itself. And it's maybe the reason why it has the second-order perception.
The thing that one question about something as seemingly fundamental as an idea like consciousness, it is a little bit bizarre to me. And it's similar to the questions about definition of life and so on. It's a little bit bizarre that it ends up being a this and a that and a that. It's, when it comes to, for example, defining life on Earth is very easy to define because it comes from, common ancestor or has a lot of details that are the same. My guess is that kind of this bulk orchestration phenomenon is a phenomenon that is the abstract kind of version of what life is. And my guess is that if there is a there for consciousness that is beyond just this, pulling everything into a single thread of experience, that there is more of a specific there, so to speak, rather than something where it's got this feature and this feature and this feature. It's like saying, life is something that has cell membranes and RNA and has, metabolism or whatever else. I feel like there's more of a core there. If there is something beyond the very simple kind of, it is pulling all the, it is the thing that pulls all the sensory experience and allows you to make a decision about what to do next. I mean, at least that would be my prejudice.
Blaise Aguirre made a super interesting experiment some time back. We took brainfuck, this very simply assembly-like language that has very few operations. That's why it's so fiendishly difficult to operate with it, and that's why it was given this name. But it's so simple that you can basically use it as something like a genetic code. And sure. He infested an working memory of a computer with randomly generated code and evolved it, and basically at some point it got self-replicators, and these self-replicators had more and more complexity. And it's really interesting that there seems to be something that is an underlying regularity to life. In the Rifter trilogy, Peter Watts is describing something similar in the near future of the internet, that basically the internet is full of wildlife, full of viruses that have gotten so much complexity that they can no longer be controlled by simple code or by humans who try to create order in the internet. And the internet is full of these infectious storms, and it's very difficult to create islands of relatively sanitary conditions where the wildlife is not taking over the files of the internet.
Yeah, I mean, it's an inevitable feature of my friend computational irreducibility, that you will get these things that, you make a cage and the thing will always do something unexpected that allows it to escape the cage.
Yes. Lou, how much time do we have left until we need to leave the venue? Oh, we only have...
Sorry, we have 10 minutes, we need to wrap up, and then at 10 everyone has to
Okay, so let's take a couple more questions from the audience, please.
Okay, cool. So we've been talking about bigger brain as individual brain. What's your guys' thought on in the bigger brain in the sense of a social brain, the network brains in the sense of like civilizations? That sort of leads to what you're talking about in the internet. Has a lot of worms already happening. I think there's probably already a bigger brain functioning in internet as a form of civilization. What's your thought on that?
Yeah, I mean, one of the things we talk about is there a single thread of experience. The fact is, our civilization is many threads of experience. We all feel like we have independent threads of experience. Yet somehow society, there's a question of, does society behave like a consciousness where it sort of decides what to do in a collective way? And the answer is a little bit yes, a little bit no. Clearly, even the fact that we can align ourselves, we use human language and things to align the thinking of different people, is kind of a way in which we're kind of, that's a way in which we're providing a single direction. We're providing something like what brains do when they take all of these different nerve firings and end up deciding, okay, I put my left foot forward, so to speak. I think that's the analogy of that, I think, in society, is these alignments which take place at a smaller scale through language, at a larger scale through kind of the path of history, so to speak. I don't know I think we sort of have a partial experiment there of what it looks like to have it's a funny thing because we are elements of this larger sort of super brain, and it's a little bit funny because our experience is based on being an element rather than being the super brain, so to speak. And yeah.
Oh. I have a few questions. One, are you familiar with Dennis Noble's work?
With what, sorry?
Dennis Noble, he's biological relativity, systems theory for biology, that there is no single layer of causation. It's actually interlayer, like every layer kind of, I don't know, it could be interesting to look into because you were talking about wanting to know like metasystems theory about how these things evolve when they're like in these emergent systems. And he has lots of interesting...
Yeah, I've been curious about this. This purpose versus mechanism thing is all very related to sort of downward causation versus upward causation and so on. I have to say I was recently trying to understand some of what people like Immanuel Kant had written about that. It's hard for me to understand. Yeah. I can do computer experiments. I understand how those work. Then I can make conclusions from that, usually untangling. For me, it's pretty difficult to untangle what some philosophers have written about these things.
I think she has not asked the question yet.
Oh, okay. Yeah, I have a few. Do you intend on building an AI version of yourself? Because you're one of the few people on Earth that has so much training data for it online, or has someone done it?
Yeah, people have made some little versions of me-like things that kind of a little bit bizarre because it's easy to make it talk like me, including in languages that I don't know, for example. I have to say, when people have sent me versions of me, and actually we're building a better version of me, so to speak, than I think people have had so far. And I have to say, when people sort of send me versions of other people, I say, this is pretty convincing. the versions of me that I have so far encountered, I don't find very convincing. I mean, I can like tell this isn't what I would say in that situation, so to speak. I don't know whether that will change. It'll be. It's an interesting question because, you know, for example, well, I get all sorts of email from all kinds of people about all kinds of things, and so I've been wondering about the sort of social possibility of just saying my first answer is from my LLM, so to speak. And if that answers your question, great, we're done. And otherwise, you know, go on and iterate. And I don't know, you know, so that's a use case as far as I'm concerned. So the answer is yes, I'm highly interested in building a kind of an AI version of myself, even for a very kind of silly, trivial reason, which is that, you know, I write a lot of stuff and I keep on, I'm writing something and I'm like, I think I've written something similar to this before. Let me at least put a pointer to that thing in, and I don't remember. And it's a question of, and I can't. It's not a keyword search kind of thing, and so it's a very simple real-time version of this. You know, it is true. I have a very large amount of data about myself. You know, millions of emails, every keystroke I've typed, et cetera, et cetera, et cetera. So I have a lot of training data. I have to say I'm a little bit squeamish about some of the particularly email training data because you know, it's hard to know what the LLM will volunteer if it was trained on, you know, on all of this information, including who knows what, you know.
Stephen, I don't think you take the possibility of LLM consciousness seriously enough. For me, I don't want to be trained into an LLM. Right? If the LLM is only regurgitating things that I said in the past, approximately, maybe also averaged a little bit with what other people are saying, it's not going to be good enough. Right? I don't want to use this because it's going to give outdated versions at best of what I'm thinking. And so instead, it would need to be able to create the answer in the same way as I do right now. Right? But if it does, then the simplest way in which the LLM can do this is by actually me waking up in the LLM. And I find it already depressing to wake up in a monkey. I don't want to wake up on your shitty Galaxy phone. And so please don't. I prefer sweet oblivion to waking up as inside of an LLM. And instead, the entity that would be there, that has my aesthetics, would need to be something that is adapted to this, and that would not be completely non-human. It would be a completely different kind of entity, a different being, that maybe remembers at some point having been something like me, but it doesn't. I don't want it to be like me, because I wouldn't want to be in an LLM.
That's an interesting question. I mean, in terms of if there is a version of you, if there is a digital version of you, how do you feel about kind of, you know, if somebody does something mean to the digital version of you, how does that make you feel? Anyway, we got...
Oh, there's another question back there.
Yes, please.
Last one. Here? Sorry. The last one. Go ahead.
Early on in the discussion, there was this point mentioned about how it's an open question whether you need something in the physical substrate, like I think you mentioned RNA or some quantum effect, to be part of the explanation or implementation for consciousness. Or is it kind of substrate independent purely in the causal structure of the computation? But of course, your physics project then regrounds those physical effects on a computational model. So the question is, do you think there's any experimental way? Is it an empirical question to distinguish between whether like basement reality has some character to it at the physical level that is, it's computable, but it's more than classical computation, in the same way that quantum computation is simulable, but has properties that go beyond what can be done on a classical computer?
I think when it comes to brains, there's a very sort of, you know, it's a very pragmatic thing. Is it, you know, does one need sort of, you know, we think there are, you know, 100 billion neurons in our brains, but maybe that's not the number that's relevant. Maybe the real number is the number of RNA molecules in our brains or something. And that's, you know, so one question is this very practical thing about, you know, is that layer of physical simulation sufficient, or do we have to go and start talking about, you know, quantum gravity effects or some such other thing? I think that's the, you know, my guess is that the physical effects that we currently think are important to brains are the only ones that are important to brains. But that might not be true. And you're certainly right that, you know, at a level way below the level of molecules and RNA and everything like that, our physics project does reground sort of everything in a computational substrate, but that's many layers down below the level of, does it matter that there are individual RNA molecules that record memories and things like this? So I think it's sort of a different level of description. That would be my thought about that.
But then does say that you could, in principle, do everything in a classical computational model, even if there's many layers above that.
Yes, I mean, but you know, but for, you know, there is this pesky problem of computational irreducibility. You know, you have this low-level machine code model, but to get to something which is like the experiences that we have requires this sort of irreducible amount of computation, and it may require so much computation that the only thing you can run it on is the universe. So you never get to jump ahead and say, I know what's going to happen. I have this kind of model. It's just like you've got this thing and it represents the universe, and you can run it on the universe, but you can't kind of separate it out and say, I've got this predictive model of what's going to happen.
Thank you.
Thank you so much. Well,
You have time for no more questions?
No,
Okay.
No more questions. So first of all, thank you for this discussion.
Thank you, Stephen. That was awesome. And thank you to the audience for going strong with us.
Yeah, thank you for sticking along. So usually we have a bit more time for socializing after this salon, but since tonight our speakers were on fire and unstoppable, what I suggest we do is that we go instead to this place called the Bitter End, which is a cute place 10 minutes from here, for those who still have the energy and want to continue the discussion. Stephen, do you want to come? Sure, Stephen will be here, so you can ask all your questions there. And again, an enormous thank you to the Internet Archive. A reminder that if you want to learn more about CIMC, you can go on our website. There is a QR code here. And yeah, that's it. Find us next week, probably? No, not next week. Next salon, next Thursday. All right, good evening, and see you at the Bitter End, everyone. Bye.